Good afternoon. So I think you guys have seen a little bit of what is happening in the industry and also in research. You heard Rishad. So this will be more like, the regular design, right? It's a tutorial, more like a class, right? And so the plan is, what I'm going to do is, because it is about the powertrain of an electric vehicle. So if you look at the powertrain of an electric vehicle, what are the things there, right? At the heart of that is actually the battery, which is the fuel tank, right? And then you need to charge the battery. So you need a converter, a charger, what we call, to charge the battery. And typically, the power is coming from the outlet, so it is AC, and the battery is at DC. So we need to actually convert that AC to DC first, rectify it, and then typically we put a DC-DC converter to control the voltage or the current across the battery, right? So we have that AC-DC, that is what we call the PFC, or three-phase inverter it could be, and then you have the isolated DC-DC. And then if you go to the other side, we drive the motor, right? So you need also a DC to AC converter or an inverter to drive the motor, right? And then, this is there, right? Yeah. And then you have another two power electronics components or converter is there. One is that smaller DC-DC converter for all your aux power, like what Rishad was talking about, a 12 volt or something. And then also you have the battery. The battery also has some power electronics in it because you need to do the balancing and all that, right? So the BMS part. So in this tutorial, we have about 4 hours of tutorial. So the plan is that we will do 1 hour on that AC to DC rectifier or the PFC stage. 1 hour we are going to do on that DC-DC, isolated DC-DC. And then 1 hour we will spend on the motor drive and 1 hour on the BMS and a little bit about the battery, right? So what I'm going to discuss today is more like the class or the regular design, how you go about that, right? You start with a bunch of specification, and then from the specification, you decide what will be the converter configuration, right? So any power electronic converter is actually a network of semiconductor devices or the switches, right? And along with some inductors, capacitors, or the passives, right? And then you have also the gate driver, and then you have a microcontroller to do the protection and all those things, right? Closed loop control and all that. So what we will do is, because it is more focused on power electronics, I will focus on the power electronics component or the hardware of it, right? So we will start in all these 3 topics that I will be doing, the motor drive, the rectifier, and also the DC-DC converter. We will start with a realistic specification where all engineers start. And then I will tell you the topology or the converter architecture that we will select out of one of them, right? And select something very popular or advanced one. And then I will tell you how to actually use it or how to employ it to do the job, right? That is the converter analysis I will a little bit talk about. That is what you will also call the switching strategy or the modulation strategy. And then I will discuss the essential closed loop control that one needs to do. That usually will happen in an embedded processor. We will not go into that, how to write the code and do that, but I tell you in essence what one needs to do, right? And then once we have done the theoretical work, we can start doing the design. So we have this realistic specification. We have now the switching strategy, we have the control, we have the topology and all that. Now we will see, how to actually select a switch, how to, go about doing the specification of the thermal system, right? And then how to decide what gate driver to use, right? And then how to select or design the inductor or select the capacitor, right? So this is the flow that we will try to do. And the thing is that, of course, in any of these things, if you go deep, it can get very, very complex. And usually this is multivariable optimization problem. But the engineers cannot just keep writing code and doing that. We have to somehow do and make things working. So what I am going to discuss based on realistic designs that we have done in our lab. So we will tell you a baseline design, right? This is a design from where the version 1 can be made, and then you can start improving on top of that, by doing more simulation, understanding it better, and all that, right? So I think it is possible. You can stop me if you don't understand something, no issues, right? But we are a little bit pressed on time, of course. And what I'm going to talk to you about, maybe if I'm doing a regular course, it will be like few classes, but I have to somehow squeeze it in short span. So, but feel free to stop me. So I am talking about the AC-DC converter, right? So your utility, that is 230 volt 50 hertz AC, from where you will take the power and charge your battery, right? So in the front, I think this was discussed in many of this, the basic configuration. You have a AC to DC, and then you have a isolated DC-DC. So right now we are focusing on the AC to DC part of the converter, that is the rectifier, right? And this is mainly, so the thing is that it is very hard to actually discuss generally, because if I discuss very generally, you don't get anything, right? So that's why what I'll do is I will take a realistic case. That is what I was talking about. So this, what I have chosen here, right, this fits into, you know, the two-wheelers are very popular. So if you look at the two-wheelers, right, you will see that on the roadside, let's say you see the Ether and all that, right, they have this Ether grid, right? They have this DC fast chargers installed, right, the DC fast chargers. So you can take your bike there and then you can charge the 48 volt battery. So we are going to see that, you know, how that DC fast charger works, right? The onboard charger is low power. The principles are same. The design can be done in the similar way, right? So 3 kilowatt. So this EVs typically, you know, the battery is a 3 kilowatt hour battery, right? So that 3 kilowatt hour battery. So this 3 kilowatt hour, this is actually the amount of fuel that is there, right? We say I am putting, you know, 30 liters of gas. So this is the same thing, right? Same thing there. This is that kilowatt hour. So with 3 kilowatt hour, I think you can go, depends upon whether you're going on a hilly terrain and all that. With a two-wheeler, you can go like somewhere around 80 to 100 kilometers, something like that. Depends upon also, you know, that kind of path you are taking and how much you are starting, stopping and all that, but approximately that, right? So you have this 3 kilowatt hour battery, and typically the battery, like, so to charge the battery, you have to actually send this 3 kilowatt hour amount of energy into it, right? So now the thing is that when you are charging with a power, it's a current, right? The current is flowing into and it is depositing the charge, right? So now if you want the charging to happen faster, you have to actually apply a higher current, or you have to have a higher power, right? So the thing is, and you know, all of us know this is one problem with electric vehicles, that, you know, your fuel car, you can fill it in 3 minutes, but it takes about an hour or something like that. Of course, these times are reducing. So mainly the restriction comes from the battery, the chemistry, how fast you can charge. But today, 3 kilowatt hour battery, when we say 1C charging capability, that means a 3 kilowatt hour battery can be maximum charge at a speed of 3 kilowatt. So if you apply a 3 kilowatt charger, a 3 kilowatt hour battery can be charged in 1 hour. So if you apply 6 kilowatt, then it should be done in half an hour, but battery may not be able to take it. But if you apply, say, 1 kilowatt, then it will take 3 hours. This is basically the way how it goes. So the fast chargers are 3 kilowatt chargers, because 1C rating. Now the thing is that the fast chargers, why the fast chargers are not inside the vehicle, why they are not the onboard chargers. The reason is that these chargers, as the power goes up, right, the converter size goes up, its weight goes up. Now in a vehicle, the size and weight is, you know, with premium, right? So that's why these big chargers that we are going to talk about today, you will see that they are wall mounted in many places, in the malls and many places, right? You must have seen in Bangalore. So we are actually talking about them. And because the power is 3 kilowatt, right, it can be actually supplied from a 15 ampere switch, 15 ampere socket, right? And that is why you have the maximum 3 kilowatt. I think it will come out about 18 or 19 ampere, something like that. So what we are doing here is that we are putting this box, which is rectifying this 50 hertz to 30 volt AC to a 400 volt DC, right? And then we are going to connect the DC to DC converter to feed it to the 48 volt, right? So now what we are going to look at that, so what this box has to do. So this box will be connecting to this and pushing the power into this and maintain the voltage to 400 volt. This is the first job. And the second job is, it is whatever the current it is drawing, that current should be sinusoidal and at unity power factor, right? So from the grid perspective, it should simply look like as if you have connected a resistance. Now, why not some other power factor? The problem is with other power factor, actually to draw the respective current, your current magnitude will be higher, so conduction losses are more. And grid people also don't like that. They will charge you for power factor. So better you draw at unity power factor, right? So, and that is why we call this kind of circuits PFC, power factor correction circuits, or PWM rectifiers, right? Where we do switching, but finally the current that we draw from here looks like a beautiful sinusoid. And also it should not have any harmonic, or it cannot be zero, right? So the specification typically is the THD, that is the harmonic content, right, should be less than 5%, right? So this is the box has to do, this is the box has to do, and we are now going to see how to do this box, right? So that is what we are going to see. So now, again, there are a large number of different ways of doing this, right? You guys must have heard about boost PFC, this bridgeless PFC, many different possible ways to do it. But today what I have selected, see, if you are in my class, I will tell you that why you not this, why that, at this power level, why you that. There is a lot of theory behind. I cannot go into that. So what I'm going to tell you is, what we will be looking at is what has become really very popular, that is called bridgeless PFC, right? We also call it totem pole PFC. So what happens is, essentially, you can see this is an H bridge. I think all of you have some kind of power electronics exposure, right? Otherwise it is a bit difficult, right? So the thing is that this is an H bridge that you can see here, right? We have 4 devices, and these are, we call legs, right? You know, we call them legs. So here in one leg I have put 2 devices, 2 MOSFETs I will put, and of course they operate in a complementary fashion, because you cannot turn both of them on, then you will short the DC bus, correct? But in the other leg you have got 2 diodes, right? And these are line frequency diodes. So they are going to switch only once in the 50 Hz cycle, or in 20 millisecond, right? 10 millisecond it is going to switch only during the zero crossing of the voltage. And this is your grid voltage, and this is your filter inductor, right? So when I talk about the box actually has this inductor, this capacitor, this switches, and this diodes, right? So we are now going to see first how to make this work, and then we will go to the design, or selecting all of this, how you do it, right? So what we want, so if this is your grid voltage, so this is 50 Hz, right? You want to actually draw a current, this is the grid current IG, which is sinusoidal and in phase. So from this perspective it looks like it is a resistance, right? Okay, so now let us see what happens when the grid current is positive, right? So if you carefully look at, this is the direction of the grid current, right? So essentially it is going like this, so it is going into this point in this leg. So from end point it is coming out, right? So it is going in when Ig is positive. When Ig is positive, it is going in here. So it should come out of this. So that is why this diode should be, there is something wrong here, I think. So when the grid current is positive, right, it is going here like that, and it has to come back, and yeah, it is the dB. This diode will be conducting, right? So that is why when current is positive and you are in the positive half of the cycle, this diode is conducting and nothing is happening on this side, right? And what we are going to do is, we are going to actually switch this one. So if you actually zoom in to this window here, right, you have this carrier and the switching that is happening, right? If you have some power electronics, you know what I'm talking about, right? And then you basically, so this is the switching signal also of this switch. So over this carrier cycle, which is much faster, maybe it is 100 kilohertz, that is what you're going to see, compared to this is 50 hertz, right? So over this cycle, what is happening is, you have this carrier, and then you are comparing a duty cycle with this carrier, and you are generating this waveform. So when this waveform is high, that means Q is on, and Q bar is off. So that means the voltage here, because remember this diode is conducting, so this point is same as this point. So when Q is on, VA voltage is actually VDC, correct? Q is on, VA voltage is VDC. And when Q is off, right, the Q bar is on, because this diode is conducting, then AN voltage is 0, right? So we can see that, right? So on an average, if you see over the switching cycle or this fast cycle, the average voltage that is being applied at this point, right, by this converter at this A point is D times VDC, right? This is the duty cycle, there is the average voltage content, average content there, right? It's a buck converter essentially, right? And then what happens is when the grid current is negative or the current is flowing like that, right? Then the current is actually going like this, and then this top diode is conducting. So when the top diode is conducting, this point is always at VDC, correct? In the negative half of the cycle, this point is always at VDC. So when I actually turn on the top switch, right, what is the voltage I am applying across this? Is 0, right? Because this switch is on, this diode is on, so I am applying 0. And when I am turning on the bottom switch, right, when I am turning on the bottom switch, that time what is happening is the voltage that I am applying here, right, is this point is 0, this point is at VDC, so the VA voltage is minus VDC, correct? So that's what I'm doing, and you can see actually when I'm in the positive half, actually I will be applying positive voltage, right? So 0 and VDC, right, I will be applying, and when I am in the negative half, I will be applying this negative voltage. So similarly, if you average out this, right, because this is the duty cycle of Q, so minus VDC is applied now for 1 minus D period of time, off time. So 1 minus D into VDC, and VDC here is negative, correct? So now the idea is that you want to actually, this is like a power system kind of situation, right? You want to actually, what you want to do, so there is a voltage source here, sinusoidal voltage source here, there is an inductance here. So you want to actually control this voltage by switching this bridge. So its amplitude and angle, so that you draw a certain amount of power, and you will be drawing this at unity power factor, right? So basically what has to happen is somehow automatically through some closed loop control, this duty cycles has to be determined to switch this converter, so that what happens, you supply the power, draw unity power factor current, and also maintain the output voltage, right? So we understand the switching strategy. Now here all we need to figure out how to generate this dt, right? If you figure out how to generate this dt, you are done, right? So let us go to the next step. Okay. So now if you look at a little bit of math, you see here that this is a sinusoidal voltage, let's say V peak sin omega t, omega is at 50 hertz, right? And then Ig is I peak sin omega t, say you have been able to do the job, right? Then what is the instantaneous power, right? So that is V peak I peak sin square omega t, right? So it is not DC, it is not DC, and if you just do a little bit of trigonometry, you can see that this power has got a DC component here, half V peak I peak, because it is unity power factor, and also there is a pulsating component of the power, whose average is 0, right? So, and if you carefully look at what has to happen is, remember Ig, this current Ig is actually I peak sin omega t, correct? So now I can actually write this, if this is the output power, that power is actually going out from the rectifier to the other side of the DC-DC. So if you call this is PO, so you can see that actually I peak I can write, it is PO by 2 V peak, right? I can write that, and then I can write also sin omega t as V peak sin omega t and divided by another V peak, right? So all I am trying to say is that, look, if you know this power that your DC-DC or whatever the load of the rectifier is drawing, right? Of course, the amplitude of that should be proportional to that power, right? Higher the power, higher the amplitude of that current should be. But the interesting thing here is I can actually see that the grid current that I need to draw is a sinusoid, it is in the same phase with the grid voltage, right? And somehow it is also proportional to the power that is going to the output of that rectifier, right? So now if you actually look at the output part of the rectifier, right, output part of the rectifier, we saw there is a capacitor there, right. So this side you have all the bridges, right. This is that capacitor. I am not showing the load here is connected, or this is the DC-DC, whatever is connected. And what I am saying is, look at this part here, right. So if you look at from this side, what is happening is that if you are assuming you are doing the control correctly, then what is happening is from this bridge, this pulsating power is coming out, because power has to be conserved. So whatever power entering from here has to come out here instantaneously. So this pulsating power that we just talked about, right, this pulsating power should be coming from the bridge to the capacitor side. So what I am saying is that, look, what is going to happen, no? This power that is coming here, assuming there is no loss in the bridges and also in that inductor, right? So that power has two components. One is the DC, another is that 100 Hertz AC component, right? So what I'm now, let us just focus on only the DC component, which will be actually transferred to your load. So your load will take this DC component, right? So now if I ask you that, you know, maintain this voltage. Remember, rectifier had to maintain the output voltage, right? So what rectifier has to do, actually whatever this load is drawing from this, it has to draw from that part of the box, right? So if I send the average power that is drawn by this guy from the grid side, I am good, I can maintain the voltage. So if you look at from the dynamics perspective, if I just write down, this is the KCL equation at this point, right? Actually this is the load current I naught, right? And this current which is coming out is P naught by VDC, right? And then this current is C dVDC dt. So essentially it is bit non-linear. You can see VDC has come down, and that is coming because of it is a boost converter and all that. I am not getting into that, not required at this point. But the thing to see here is that, you know, what you have to do, if you don't want this voltage to change, you have to match the output with the input, correct? That power you need to draw. So basically what will happen, if I say this from the closed loop perspective, what you have to do is, if say you want to maintain this voltage VDC star, that is 400 volt, so you take the feedback, right? You take the feedback, you compute the error difference, and then you pass it through the controller. What controller should tell you? What should be the power come from that side of the box? Controller should tell you that. Controller should tell you what is the DC component of that power, because that is the power going to the other side. And if I don't keep the balance, the capacitor voltage will change, right? So that is the closed loop control, right? So you understand this, and this part what I am showing is the plant. This is basically the flow diagram of this, right? This is your this minus this P naught into by BDC, and then 1 by SC is the plant, and then you have this, like how you write it in the control system, right? This is your plant, this is your controller, right? So all I am saying is that I have to maintain VDC star 400 volt. So what I am going to do is, I am going to take the feedback, of course, right? Put it through a controller. Controller tell me what should be that DC component of the power that I am drawing, right? Okay. Now let us look at the and this PO should go in, and then, you know, things will be fine, right? But, you know, there is a dot here in between, right? We don't know how that PO is going to translate into this, or where I am going to put it, right? So next let us look at the dynamics on the input side of the grid. So if you look at, remember we had this picture here, you have this sinusoidal voltage source, that is your grid, then you had the inductor, and here is the voltage that you are controlling by controlling the duty cycle, right? So if you look at, so this is that average voltage, right? D into VDC when IG is positive, and the other way, right? So if you write down this equation, this is actually VG, LG ddt of IG. This is the KVL equation, right? Simple KVL equation here, right? So what is happening is that, you know, if you want to, remember you wanted to have a sinusoidal current, right? So to maintain a sinusoidal current, let's say you have the reference. Let's say you somehow know what that sinusoidal current is. say you know what that sinusoidal current is, then what you will do again, you will actually take the feedback. See, this is not VDC, this is incorrectly written, it should be IG here. Okay. This is just the representation of this in the box form, right? So you take the feedback, you calculate the error, and this is your current controller. What your current controller will tell you? What this voltage, inverter voltage you should apply to flow that current. See, it is very simple. I have one source in one side, I have an inductor, and I have a control variable source in another side. If you want a particular current to flow, you have to actually change that knob. You have to actually change this voltage, right? So your closed loop control should give you this voltage, right? But now, so is this clear? This makes sense? Yeah? Go ahead. I have not come to modulation yet. Modulation is you have to find out D, right? We have not come to that yet. Still the problem is not completely solved. We are step by step going towards it. So there are two problems. One is that I need to maintain the output voltage and I need to shape the current sinusoidal in power factor, right? So that's what we are seeing how to do that with a closed loop control. And finally, your control is on those duty cycles. Go ahead.
So basically, that power varies, no? Based on the load, the power varies.
Correct.
So based on that, we have to adjust the power so that the voltage has
to be. Correct. So if I change the load here, this loop will respond, right? If I just increase the power, the voltage will drop on the capacitor. It will see that happening, and the controller will say, okay, increase the power to restore the voltage, right? So now you got these two loops, right? Still we don't know how to get the duty cycle. Now let us see how to do it, right? So now let us look at this output voltage loop, right? Output voltage loop was telling you what is the P0 is, right? Output voltage loop was telling you what should be the DC power, right? And remember we said that, you know, IG, when you are drawing this nicely, everything is happening right, IG was, see we figured out, remember PO into VGT by this 1 by V peak square, right? So now I am sensing the grid voltage, and from the control loop, outer voltage control loop, I am getting P0. So all I have to do is multiply these two guys, right? That should give me my grid current reference for the current loop. And current loop will tell me what is the average voltage that you have to make, VA, right? And VA to D we have already seen the relationship. And that's how I am going to switch the converter, right? So here is the solution. So the thing is that it is actually giving you P0. See, in some books you may see people will actually divide it by 1 by 2 V peak square, but not required. Closed loop control takes care of that, right? So actually instead of PO, it will generate the output of this loop will give you automatically the scaling factor of 2 V peak square. So that is the 230 volt, right? That number. And then you multiply, this is a multiplier block, you multiply that with your grid voltage. So you get the sinusoidal grid current reference, right? And that sinusoidal grid current reference, you can feed it to your inner current control loop. And this inner current control loop actually tells you what is the average voltage that needs to be applied. And once you know the average voltage, you can calculate the duty cycle. And once you calculate the duty cycle, and you know, remember the duty cycles were different, so I have just written it in the other way. There I wrote average voltage in terms of duty cycle. Here I have just done the opposite, right? So I can calculate the duty cycle. So when the grid current is high, whatever the controller output is coming, I will divide it by VDC. VDC may be changing a little bit, no problem. You have a nominal value, you know, loop will take care of that, right? So you do that and you get the duty cycle. Then you compare that here, you compare that, you get the pulses and you apply it, right? So just to summarize, what we have understood is how a totem pole PFC works, right? Now what I am going to do is, because now I know the modulation, I know the specification, I know the converter and all that, right? The next step is now I am ready to do some design, right? So while we start the design, you can take a 2-minute break and get questions from you. Yes, yes. This one or the previous one? This one, right? So see, remember the outer voltage loop? Outer voltage loop here, right? The outer voltage loop is working on this principle, right? It will tell you what should be the power that I need to draw from the AC side, right? And then I did this calculation earlier that the grid current, if you are drawing a P0 power, average power, that is going into the other side of the rectifier, if you are drawing that power, what should be the grid current reference, right? And then I told you using this part of the converter, I can actually shape the grid current, right? See, if you look at this, right, I have a constant voltage source here and an impedance. I want to shape this current by adjusting this voltage. So my closed loop control should tell me what is that voltage I should apply. That is my control input, right? But that is good. But the thing is you have to get the current reference, right? So that current reference I am computing from the voltage loop, because voltage loop is telling me what should be the power. And also I have sensed the grid voltage, so I know the phase of the grid voltage. So I multiply the grid voltage with the DC power reference that is coming from my outer voltage loop, and I get the grid current reference, right? So that is exactly what we are doing here, right? So this is your outer voltage loop. Outer voltage loop told you what is P0, right? See, here I am dividing it by 2 Vp square, right? But in actual implementation it is not required. Closed loop control will understand, and instead of giving you PO, it will give you PO by 2 Vp square. That is the closed loop control, second, right? And then you multiply with Vg, then you will get the current reference, right? Grid current reference, and then the inner current controller will tell you what should be the voltage that you should apply to make that current like that, correct? Yeah, go ahead.
Reference frame. In which reference frame will do this one?
It is single phase. We are doing this in the regular ABC reference frame. So only thing is that, you know, here what will happen is that, see, there are some more stuff is there, everything difficult. But see, the thing is that instead of DC, this current controller has to actually track a AC. So typically you will use a PR controller, proportional resonant controller, right? But you can actually go to DQ and make it DC, and then it is possible to do if you have a PLL and all that. But this is simple thing to do.
And linearization, sir?
Linearization, we don't need to do linearization for this because this is, not non-linear. But this output voltage, that is the, you have seen, no, here, this output voltage, this is non-linear because VDC is appearing below this, right? So this always works on small signal. Now the thing is whether you linearize, you don't linearize, control loop will give you that, right? So only thing is that it will not work for a large change in the load. So that is a problem, you know, of any rectifier. And that is why you need to have that other DC-DC there. It's basically a boost converter. You are controlling on the voltage, output voltage. It's non-linear. Oh, okay, okay. So, so the thing is the original circuit, right, from where this all originated was this circuit, right? So, yeah, so you have the AC here, right? Sorry, not here. Here, and then you know you rectify this, right? And then what you do is this is the boost PFC, right? Operation principle exactly the same, right? Exactly the same. But what happens if you look at the current? Here the current is always flowing through these two diodes, and also either this diode or this switch, right? So I have 3 devices in conduction, and so I have more loss. But if you look at this topology, always only 2 switches are operating, right? And here another interesting thing is that actually you can make Actually, this is a variation of full bridge. I mean, we can discuss this. It will take a longer time. But, you know, you can actually just put diodes here. It is possible. You can see that it is possible. But if you want a power factor, it is not possible with diode. You have to have switches here. Right? So that is the chief advantage. And the thing is that I am just using one switch. That is the like there, right? Just one switch control I am doing. And correct. Both are happening. Right?
Sir, sorry.
Go ahead.
So your correction was instead of VDC, it should be IG on the next graph, no?
Yeah, that was a mistake, I think. Okay. See, this should be IG here because, you know, just flow diagram if you write, yes. This should be IG. There's a mistake.
So next, so I can see one more VG of T after CI of S, one block.
Oh, so what we are doing is that actually if you want, you can do this. You can do a feed forward cancellation, right? See, in actual circuit, what is happening is this VA is going, right? So VA minus VG is LDI dt. So 1 by LS is IG. So one thing you can do is, so if you don't put this, no problem. It will simply track this, right? But the thing is that suddenly there could be some grid variation may happen, and sudden fluctuation can happen. So what we do is, anyway we are sensing the grid voltage, so we can actually cancel it. So whatever is coming out from the rectifier, control, I can just subtract this, right? Actually this is subtraction, here it should be addition. This is also a mistake here. So if you add this, what happens if you look at from this loop perspective, you have just cancelled the, this is actually a disturbance in the loop. You have just cancelled it. So, and this loop becomes very simple. It's just an inductor then, right? But it is not necessarily that you have to cancel it.
You mentioned feed forward.
Feed forward. This is the feed forward cancellation, right? This is the feed forward cancellation of grid voltage. Some positive, negative, maybe. See, the way this is, this should be VG is, I think there is a mistake here, right?
Sir?
But the KVL equation.
Sir, in boost, so many topologies are there. Interleaved boost PFC, totem pole boost PFC, bridgeless totem pole boost PFC. So where we use these topologies, like if we are using low power applications, so we prefer boost, conventional boost or totem pole. If we are going for high power applications, so which is preferable?
Okay. So the thing is that actually which type you use very much depends upon your cost and also what is the power level you are doing it, right? So the thing is that, say for example, the problem in this particular circuit, right? If you use silicon MOSFET, typically you see, I will try to answer this question quickly because it is a long answer to this question. So typically what happens is that if you are actually using this with a MOSFET, right? Typically it is silicon MOSFET. They are available at below 600 volt, right? The thing is that this guy has a bad diode which has a reverse recovery problem, right? So you have to always use this silicon carbide diode here, right? Yes, and this MOSFET you have to use, right? See, if you don't have silicon carbide MOSFET, if you try to use another MOSFET here, right, boost PFC will not give you good result, right? There is a problem. See, this particular topology is actually not possible with silicon MOSFETs, what I just discussed. Because here, both switch, if you put silicon MOSFET, you are going to see the reverse recovery. Whenever one guy turns off, right, you will see the reverse because of the bad body diode. But right now, the design that I'm going to talk about, we are using gallium nitride devices, which does not have a diode, and reverse recovery charges are almost zero. Where? No. See, the thing is that, see, instead of this, if you put a MOSFET here, you are going to see reverse recovery problem. See, every switching cycle that is going to happen. See, I am not talking about this diode. These are line frequency diodes. These are line frequency diodes.
Sir, if we are using gain devices, so again we face issue with EMI issues. Like if we are going for high frequency, then it's also an issue.
Yeah, see, the engineering is all about that, right? So we have to actually, why we want to go high frequency, because I will show you some design. This choke is very big. The devices are very small, but this choke is very big, right? So I will talk about a project in which we had to make this very small. So only way you can do that, you go increase the frequency is 2 pi f, or 2 pi of this period, right? So you can actually derive this, right? So once I have this, I can actually, that is why that fs by 2 pi is coming there, right? So it is easy. You can actually integrate and you can find out the switching loss, right? So now, say for example, let us take a sample example where I am saying the switching frequency is 125 kilohertz. Let's take that and let's see whether it works or not, or what happens there, right? So if you do that actually, then you get this loss about 6.5 watts practically for this device. So now, see, data sheet will not give you at this particular voltage and current level, right? Data sheet can give you some other voltage level with some other gate resistance and all that, right? So then what happens is that if you actually look at, if I just go here, now I am trying to calculate the total loss here, right? So now this 2 just works like a resistance, right? No switching is there, so it is only resistance. So the current, the sinusoidal current is actually carried by these 2. So it's the RDS1 is the, the resistance, forward drop resistance. Then this I square RMS into R is the loss, conduction loss in this. And here half the time this conducts, half the time this conducts, right? So basically always one resistance is conducting. So it is I square R. And in these 2 devices also, always one device is conducting, right? One device is conducting the current, and that is RDS on, right? And they have the same RDS on, right? So then here also the conduction loss in this full arm is actually I square into RDS on, right? It's simple, it's not that complicated, right? And then we have also the energy loss here, switching loss we have computed. So if you do that, this is the conduction loss on the high frequency side. This is per device, because whatever this by half will be on each device, because always I square R is either this or that, but the devices have symmetry because of the sinusoid, right? So it is the half of that, and then you like that you can get also the conduction loss for the high frequency bridge. I think this is the low frequency bridge, no? This is wrong, this is not HF, it is LF. And you can see that because this RDS1 was less for that, how less this is compared to this. It is almost 3 times more on the gallium nitride. So the high frequency then switching loss plus conduction loss, and then this is coming out to be about 8 watt. So this 8 watt is per device or the full, this per device. So 2 device it will be about 16 watt. Remember I told you, about 30 watt is my limit, right? So this is about 16 watt, and then the low frequency, where is the low frequency? Only this, right? This is about 0.7 watt, it is very small. So the most of the loss is on the high frequency side. So you can see the bridge is having about 10 watt of loss. So that means actually you can increase the switching frequency now. If your limit is to go up to 30 watt, you can increase switching frequency here. But we have kept it up to this, right? So actually what is the 1%? Is 3 kilowatt, right? Huh? 30 watt. So 30 watt is so I have to also put something on the choke. Choke also going to see some loss, right? So this is where, see, this is what the calculation we do for many devices from different vendors, right? Then finally we see where we can get the best frequency, highest frequency we can go with my budgeted loss, right? So that's how the design goes, right? Also there is another thing is junction temperature. Say for example, you may say that, okay, I am only focusing on power density, I don't care about loss, increase the switching frequency, but with the switching frequency your losses are going to increase. Even if you don't care about efficiency, your junction temperature is going to increase. So there is also another limit comes from there. So you can do a simple calculation like this. So you know that per device this is the loss coming out, and from the device datasheet you can figure out what is the junction to case thermal resistance, right? Say for example, we read this from the GAN datasheet, And then you can assume a particular heat sink temperature. Typically, if it is air cooled, we can take 80 C just for the calculation. Later, you can change that, right? And you can see that in that case, the junction temperature is about 98 degrees Celsius if we take 80 C here, right? And your the rate, it is 150 C device, right? So if the device maximum junction temperature is 150, typically you can do a 30% derating, right? We do more than that because we do not know these devices, so we do more. So you can see here it is about 100 C. So that means this is telling me if I use this device, I still can go up on my switching frequency, right? Efficiency will little bit reduce, but junction temperature will remain within the limit. We did not do this calculation for the low frequencies because the losses are just 1 watt, they are 0.7 watt or something, right? So that is how you do the bridge, and also you select the driver. So I cannot go into that detail. So driver, basically you select how, so actually here data sheets are there. So this is the driver, this is I think Silicon Lab driver we are using, right? SI driver we are using. So you have to see essentially few things. One is that what is the voltage levels that it has to go, right? So for example, this particular GAN device, I think this is 6 volt and minus 3 volt, right? Something like that you have to apply. So your driver should be able to handle that kind of voltage, and also the peak current that it has to supply, because whenever you are switching, you are charging that gate source capacitance. So initially when it is discharged, it will be just a short circuit. So this applied voltage by the driver divided by the resistance, gate resistance, is that peak current. So you need to look at that. You also need to look at what is the slew rate, how fast it can go, because here I think the switching times are in few nanoseconds or few tenths of nanosecond. So that also you have to be cognizant about. So this is actually the bridges boards that was made by the students that you can see actually. And then Rishad was talking about this, right? These black ones are those Murata, I think Murata or something else we are using here, right? Those isolated power supplies. But the devices are really small. You can see this is the silicon carbide. Actually, GaN devices are on the other side, I think, right? So these are really tiny. Here in-house. So layout is also, there are a lot of tricks and a lot of things are there that we are not, yes, it is not easy. So that also, that I am not getting into. So semiconductor loss, if you put together all of that, it is about 18 watt, something like close to. So we can go only 30 watt we can give to the choke if we want just 1% loss, right? I mean 10 watt we can give to the choke. So this some calculation. So when you are doing a calculation like that, you're you are in the right place in the design, right? So now I will not go in huge detail here. So now we'll look at the choke, right? So I think all of you have studied buck converter, right? So how we decide the value of the inductor? By looking at the peak-to-peak ripple. So here what is happening is I am applying, in one side I have a sinusoidal voltage of the choke, if you remember, and on the other side I have a switching voltage, right? In buck converter, that other side voltage is DC, not sinusoidal, but the pole side voltage is switching, right? So typically what happens is that we tell you, okay, keep the ripple, peak to peak ripple 20% of your load current, right? That is how you do buck converter design. So now, but here what will happen is your ripple will also depend upon your sin theta, because it is the sinusoidally changing, no? The other side voltage. Your duty cycle is also sinusoidally changing, that you have seen, right? So that means here the ripple current, if you actually look at the current, the ripple current will be a function of theta as it moves, right? So what we have to do is we have to actually figure out at which theta the ripple becomes maximum, right? So it is, you can write that as a function of theta, and then you can differentiate and you can find out what theta, actually here it is at this theta. See, this AM is the modulation index, which is the peak of the output AC voltage to the DC bus voltage, right? And this formula actually holds when M is greater than 0.5, less than 0.5 can be done. I think there is some problem like that is done in Ericsson's book. You can look up, right? So, and here what we said is, what should happen? I want my peak to peak ripple. I have a rated current. 20% of the peak. I want that, right? So then I can actually figure out what will be my inductance value. So that's how we figured out here. It's about 130 microhenry. Now, if you don't want to do that much analysis, you can just put it together a simulation. Simulation you can check where the maximum is happening, and then you can do the same thing. Possible, right? And of course, another thing is there, that aim is also there. So aim is your, I told you, no, grid voltage is changing. DC bus voltage is 400 volt, grid voltage is changing. So you have to also see at where is the aim, this also becomes maximum, right? So you have to take that, and that's how you have to design the, the inductor value. So now you got the inductor value. You have to actually calculate the RMS current to do the design. Now RMS current also can be calculated. It will have a fundamental component, that is easy RMS. And then you have this switching frequency. If you say 20%, that's quite significant. So you have to calculate that. That calculation is again a bit tedious because it is changing with theta and all that, right? So, but one can do that, right, and do that calculation. So you can actually see though here in this particular case, because the frequency is high, no, this RMS, switching RMS is very small compared to this. So you can straight away, like if your frequency is somewhere around more than 60, 70 kilohertz, you can neglect that ripple in the RMS because they quadratically add, right? So, so this is the RMS current, that is the peak current. Now once you know the RMS current, you know the peak current, you know the inductor value, you can select an inductor or you can design an inductor. So that is what we have done. I think this is an inductor I think we bought off the shelf. And this inductor is very large, that we'll see you in a picture. Huh? Capital M is actually V peak by VDC. That is the modulation index. Yeah, go ahead.
How do we find the core loss of this inductor? Is it significant?
Right. See, the thing is that that we didn't put here. So actually, if you go to this guy's website, there are two ways. One is that they have some loss calculator. So because they know the material, and you give the maximum peak to peak or the profile you give, it will calculate that for you. And other method is that actually you can use for the core loss, you can use the improved Steinmetz equation. I mean, that is still, I think that there is a lot of error with that. With that also you can calculate, right? So how much was the core loss they told here? You remember? But you remember the loss number analytically, I mean, through their tool computed loss? About 10 watt total. And I think the core loss component is small here because what is happening, no, this is not the AC choke. I mean AC, but your big AC is at 50 hertz. So your small, that high frequency stuff is, the amplitude is small. So core loss is small, that's why. It's mostly conduction loss. So we got the inductor now, and then the capacitor, right? So now here the interesting thing is that this capacitor that is there in the output, right? It has to actually take the switching frequency current. Actually it has to also take high frequency switching current, right? That I am not discussing. That you have to put some tantalum ceramic capacitor which will see current changing in nanosecond, right? And those are called decoupling capacitance. They have to be put very close to the bridge. And then you have the switching frequency because the current, if you see on the other side, it will be switching current, right? It is a boost converter, right? This side current is DC, but the capacitor current is switching, right? So there is a switching frequency component of that current, right? So there what you have to do is, there also you can play that game that like we do in buck converter, right? So buck converter, you know that this is the inductor peak to peak current, and you think that the entire peak to peak current will go into the capacitor. So then for a particular voltage, allowed voltage ripple, peak to peak voltage ripple, you can find out what should be the capacitor value. This is exactly how you do buck converter. So here say we say 1% ripple, and I told you, already we have decided that peak to peak is 20% maximum. You say that entire 20% is going into the cap. So then what should be that value? So that is how you will find out the switching frequency component of the capacitor. So those capacitors should have a resonant frequency high, so that it will take out all your 125 kilohertz stuff, right? And also the RMS current you can find out from the switching frequency, that all the switching frequency inductor current is flowing through that, right? Then you know the RMS current. So if a capacitor, I know at what is the value, if I know the RMS current through that capacitor, and if I know what frequency it has to operate, I can select the capacitor. And then this capacitor is going to be a film capacitor. I think that we have not put here, right? Okay. But then the big capacitor. So now what I told you before, right? See, look, this pulsating power, right? There is a, from the AC side, this is the power coming in. So if there is no loss, this is the DC component of the power that is going into the load. But what is happening to this guy, right? There is a pulsating component of the power that is called 100 hertz power, right? So that 100 hertz power, our idea is, so that 100 hertz power will be consumed in this capacitor, right? You want to make another capacitor which will take that 100 hertz current, right? So if you look at this, right? So remember the that this second harmonic power that was half V peak I peak into cos 2 omega t. If you remember, that formula was there, right? So now if you now half V peak I peak is P naught, right? That is the power, 3 kilowatt that we are talking about. Now if you divide that power by DC bus voltage, because this is the DC bus voltage is almost DC bus, it is fixing that voltage. So the power by voltage is the current. So this is the second harmonic component of the current that is flowing through, and it is steady state sinusoidal current, right? So there will be a second harmonic ripple on the voltage, right? So if this is the current, so this is the impedance of that capacitor, right? 1 by omega c, right? That is the impedance, and here it is 2f, right? 2 pi f, but f is 100, f is 50, so I have written here 4 pi f. So this into capacitance is the second harmonic voltage ripple, right? So actually in simulation beautifully you can see this. I mean, if you do the calculation, right, and you look at the actually the voltage, you will see that second harmonic ripple, or if you look at the spectrum, you will see that this is matching, right? So now if I say, you know, the second harmonic voltage ripple should be at this, should be this much percentage, let us say it is 10%, right? That tells you actually what should be this capacitance that you have to put, right? So typically what happens is that we don't want to make it 1% or something, then the capacitor will be very large. And if you have a large capacitor, there are a few problems. One is you have to put electrolytic to use to make it compact. Electrolytic has got reliability issues, and also the ESR is bad for electrolytic, right? So that is why we are allowing almost 10% ripple, but I am okay because it is inside the charger, right? I am going to have a DC-DC converter. That DC-DC converter will reject this 10% ripple. In fact, you can have little more ripple also, because your output battery should not see this thing, right? So my converter will reject that, whatever is there here. But if this is your output, then you have to actually put lot more capacitor, right? So this is where we almost complete our AC-DC discussion, right? So I'll just summarize. We need a rectifier, AC-DC rectifier. The job of that rectifier is to rectify the AC voltage to a DC voltage, maintain that DC voltage, that is input to your DC-DC, and the power should be drawn in beautiful sine wave at the same power factor, right? I told you one most popular and advanced topology, that is bridgeless totem pole PFC. And I told you the working of the bridgeless totem pole PFC, how to switch, where are the inductor, where is the capacitor, where are the switches. I told you how to switch, and then I told you how to find out the duty cycle using closed loop control, right? And once we have that, that was purely academic, and then we came to that, okay, I have the switches, inductor, capacitor, this is the specification, how I go about finding out the devices and answer the most important question, that how I decide switching frequency. So that is what I have shown you, right, with an example. So now this converter actually we have built. Okay, so there is also this EMI filter is there, I am not going into this, okay. So this is the converter that you can see that we have built, right? This is some waveform, and the peak efficiency is about 1.5 kilowatt. It goes to 98.5%. It sort of matches. I think that our estimation in the choke is wrong because it is calculated using that third party thing. So there is another, see, we expect it is 1%, but I think it is more than 1%. Another 0.5% is happening somewhere that we do not know. We are trying to improve on that. So now the thing is that, look, this converter is the 3 kilowatt DC fast charger. And if you have seen this 3 kilowatt DC fast charger in Bangalore, they are this big, wall mounted. But you see the size of this converter? This is because of gallium nitride we could do this. If you use regular silicon superjunction and use basically the dual boost PFC, right, your size will be big. You will not be able to switch more than 40 kilohertz, right? So that is why you have that big converter. So this is a project with Ethar scooters. So Ethar told us that, you know, can you make this DC fast charger? So right now what happens is, what they give is, they give you a portable charger, which is like this big, and it is like 800 watt, say 1 kilowatt. So it will take you 3 hours to charge at your home. So it is portable, right? Because there is no space in the scooter. So what you do is, when you are going to get vegetable, right, that time you keep the charger at home, get vegetable. And when you are going to friend's place, spend the night, you take the charger and charge there. That is what is happening now. And then you have all these big chargers, right? So now you think about this. This charger is going to be like this brick, that 3 kilowatt DC fast charger. And the idea is that Ethar will actually mount it in the back of the front wheel, where you put 2 of your feet there, right? So it's tiny and it can be put there. And then, you know, you can go to grocery and do all that. You have to forget about your charger. And no DC charger. And there is also this thing, you have to figure out where are this. Though Ethar, I know it's all connected vehicles. They will show you in the map where are the charging points, but there are not many, right? So the thing is that the spec they gave us is less than 1%. Less than 1%. So that is the DC-DC that I am going to talk about.
So regarding the digital,
this is only the PFC part, AC-DC part.
So
yeah, it is very much changes. So this is actually a soft magnetic material. I didn't say all that. So what happens is that at the high current, inductance comes down to 130 microhenry. It is like this, correct.
So since it's a digital control, at what frequency you are, like, it's recommended to measure the DC voltage and the line voltage or the current, like what rate? If it is 125 kilohertz, each switching frequency, it's recommended to read the values or for digital control.
See, the thing is that, see, my switching frequency is high, but my control loop bandwidths are not high, right? I don't have to. I can sample slowly because it's all 50 and 60 hertz, right? And I am not looking at high transient load in this particular case. Did I answer your question? See, my control loop calculation, I understand. What you are saying is that if your switching frequency goes up, your control loop calculations also has to be finished faster, right? But the thing is, what I am saying, we don't have to actually do that. I can the duty cycles may get updated slowly. Switching frequency I am increasing because I want to make the choke small.
Another doubt is,
but this 125 kilohertz, we can do that, man. We can do that duty cycle calculation, both the loops we can run. So we are using this 79D TI 28X 3879D. So that, I think that can do 200 megahertz. And with that, we can finish all the calculations.
Regarding one more thing, regarding the inductor calculation,
regarding?
The choke, PFC choke calculation, the peak current, you ignored that ripple peak. So basically, so that at the peak of the sine wave,
Huh.
So suppose if we are not including that in the peak value. So
No,
basically,
see, when I am calculating the peak current, I am actually doing a pessimistic. So you know what is happening. I know what you are saying. So you have the current. So that current you can take the lowest line, the worst case. If you do this correctly, you take the lowest line. But you know that theta, it depends upon theta, right? So it does not happen at the peak. So there is a low frequency and there is a high frequency going on that. So you may, if the peak to peak of the high frequency coincides with the peak of the low frequency, then you will get the maximum. So that is what we are doing here. We just added that, I think. So that is the worst case. But in actual case, that will not happen. But you can all find out that from simulation or by doing calculation.
last doubt is that since you selected 650 volt devices, GaN devices, but when it comes to the capacitor, it's just 500 volt. Since you are the
Capacitor is
since the pitch, output came at that capacitor 500 volt rating.
okay.
So that some derating or something has to be done, or for like.
See, the thing is that what we thought is that see the capacitors, right? This is not seeing any high frequency stuff. All your high frequency is taken care that we are not showing here with the high frequency MLCC decoupling caps, right? So this guy is only low frequency, man, and I have 10% on top of that. So I have almost 100 volt band. Actually, it is not 400 volt. No, what is the voltage we are maintaining? 425, and then you have the 10% ripple on it. I think it is okay. I think, but you can use a little bigger one. It's the only PFC stage. DC-DC we have not discussed. That we will discuss now. Huh? No, I will discuss that. That was our second part. The presentation is here. Presentation. Put it. Yeah. This is the EMI filter part. Yeah, you see that one. So this is the EMI filter. So AC is coming here. This is actually the GaN high frequency switch. So we have this copper plate connected in the back. So basically it will be connected with the enclosure, right? And enclosure will be forced cooled. This is conducted emission. Conducted emission.
CISPR 25. Okay. Any issues related to radiated emissions in this?
Issues related to?
Radiated emissions.
Radiated emission we have not done yet, man.
Okay.
We are still developing. We are not done. Certification is not done yet. But we have used Listen to calculate that, like with that standard, EMC standard, that we have checked this filter is working fine at 125 kilohertz. So now we have another version we have made because still this is big. So we are doing this interleaving PFC. So where you can interleave and the chokes can become even smaller. So you can see when you go to our lab, you will see this converters are there.
Thank you.
Thermal the switch, how it has been managed? Thermals and the switch.
Thermals, huh. So the thing is that right now what is happening is that we have this, we have computed this, no? We know how much power that will go to the thermal, right? And what we have been told is, so you can see here, so this is the GaN board is there on the other side of this copper plate. And this copper plate is maintained at 80 C by forced air cooling. So in the actual project, it will be air cooled.
And one more thing, while calculating
And we have done simulation so that we know it works.
You had mentioned based on current level or what we need to calculate. But RDSN has considered a based just whatever is given in the data sheet. Even RDSN has been considered based on what temperature level we are monitoring, right? It has considered directly 10 milliohm something.
So the RDS1 you will get at high temperature also. They will give you 100
The
C.
data sheet it has mentioned.
Correct. Data sheet does mention. So we have taken this from the data sheet. Yes.
Okay.
This is This RDS1 is taken from the datasheet at the higher
Maximum.
junction temperature. I
Okay.
think 100C they have given this.
Energy loss also we can take same, right? So why we need to calculate again?
Sorry, I cannot hear you.
From the data sheet, we already have power dissipation or T and turn on time for MOSFETs.
But those things doesn't work, you
So
know.
you should
So
mention for
we are not discussing that. So I have one student worked on just on this. So the thing is that your T on T off and how, see, first thing is T on T off and also how your voltage and current actually changes,
Yes.
right? They depend upon a complex dynamics. They are not like you know, triangle and you do have BDC and that and T, and they are also a strong function of your parasitic inductance and capacitance.
Okay.
So the thing is that if you are just taking from the data sheet also whatever is given, is at a particular operating condition. Nowadays they have started mentioning what was that LG
Yes,
or
yes.
whatever the LDs or you know those inductances and all that, right? So if you change from there, it will change quite a bit.
And one more thing, double pulse test usually do it for characterization of devices.
Uh-huh.
It's not for, if I'm wrong, just correct me. We never use it for just calculating energy loss.
No, we do. We do.
So usually,
That is one of the most important things.
usually for characterization, when they do it for after the design, they do double pulse test for check the conditions, extreme conditions.
Right. So double pulse test, you are checking the over voltage, current
Yes.
overshoot, voltage overshoot. Also, you are calculating the loss.
Okay.
Some waveform is there. Correct. This waveform, there is some oscillation here, but you can see the double pulse test setups are also there.
Okay.
See, the thing is that we do some other type of research in which the problem here, see, even beware of the simulation also. Simulation, what they do is they just assume a eon and then just
saw.
multiply and give you that. They scale with the voltage and current.
Linear.
That is incorrect. That gives you an error in the ballpark of 30-40%,
Okay.
right? So, see, major challenge, one thing is that getting the GANs working at that frequency, right? That is challenging, the layout and all that. And another challenging thing is that the inductor is so big.
Sir, and one more thing, in the inductor, you had mentioned that switching ripple current. So usually when we design for any inductor or something, we consider as an average current, right? What is the use of calculating that value? Switching ripple current something. So why do we need, or do we use that anywhere for any?
No, the thing is that, see, it is buck converter, right? You forget about this, buck converter. So the buck converter, switching, see, its filtering is done by inductor and capacitor. If you say I will allow higher ripple on the inductor, then the capacitor size will increase,
Yes.
right? So that's why I need to do the ripple calculation, right?
Oh, this is for capacitor calculation.
No, not only capacitor, selecting the value of inductor.
This is just an switching ripple.
Huh.
You are telling.
See,
you are we
again
need
buck
to
converter,
consider an
right?
average.
Buck converter, if you know the average current, this
We
average
consider
current here
average.
sinusoidal.
Yes.
That's the difference. Average current there is DC, here the average current is low frequency AC. But on top of that I have this high frequency ripple,
Okay.
right? So to minimize that ripple, I select my L value based on how much ripple I will allow.
Okay.
Lower the L, higher the ripple,
Understood.
correct? So for that I need to do this calculation. If you don't do the calculation, it's fine. You can find out through simulation.
Okay. Thank you, sir.
Yeah, see, we have chosen it so that it is bit high. I mean, I think, see, this we have not designed, right? This off-the-shelf part we have taken. So I think that it is derated from the peak to, I think, 7%. It's a soft core. It is soft core. Soft core. It's ferrite, I think, soft core. Okay. Oh, thank you. Thank you. It's a complex topic, short time, right, doing this project. But if you get the big point, right, that's all. Like, you know, where to approach, how to go about and things like that. So now I will discuss the, I know all of us want tea, but I will discuss little bit the DC-DC. If I left, some leftover is there, tomorrow we will do. Okay. So now you have to have that isolated DC-DC, right? So I got 400, I have to go to 48, right? So how I'm going to do it, right? So the thing is that the basic idea for all of this is this, that, you know, the moment power goes beyond 1 kilowatt, you cannot do flyback. Isolation is required from the battery charging perspective. So you have to do some kind of a full bridge solution. You don't want to do forward and all that. It will be, you know, big and lossy. So you have to do a full bridge. So in full bridge, what happens? What happens in full bridge is basically a buck converter, right? So all you do is that buck converter that you want to change the voltage, you basically switch that to a high frequency, right? So we take a H bridge, you make a quasi square wave at high frequency. That quasi square wave duty cycle is what your buck converter duty cycle. Then you pass it through the transformer, then you rectify it, then it becomes a unipolar pulsating waveform with the required duty cycle, and that is same as your average voltage once you pass it through a LC filter, right? That is the full bridge converter, all of us know. And the thing is that full bridge converter is a very good converter because it's a PWM converter, and you know, essentially for a PWM converter, the gain of the converter is independent of load. In a buck converter, the gain is independent of load. It is duty cycle into DC bus voltage, right? But of course it depends upon, because your inductor is not ideal, your switches are not ideal, so current, it will flow. So you need a closed loop control to keep the duty output voltage within some specified limit. But if you take resonant converter or some other converter, there what happens is that the output or the gain of the converter highly depends upon your load and makes it quite non-linear, difficult to control, and a lot of other things. See, even this inverter that we just discussed, I mean the rectifier that we just discussed, it is actually a buck converter. If you see, I am just making that voltage on this side of the inductor by chopping that through that bridge, right? And adjusting that voltage to get the power flow, right? That is what we just discussed, right? And there also, the gain of the converter is actually independent of the loading. Now, what happens is that, the thing is that most of the applications for last almost 30 years, anything more than 1 kilowatt, we have used what is called phase shifted full bridge or full bridge converter. But what happened lately is that full bridge converter has some other problems, right? So one of the problem is that, full bridge converter assumes that the transformer has no inductance. It's an ideal transformer, but you get a drop there because there is leakage there, right? So, and if it is, a high leakage transformer with a lot of current, you may see a huge drop, right? It's not good, it's difficult. And then there are some other problems, that there are some ringing issues are there and all that. You need to put a snubber circuit because of the output bridge, the diodes has this capacitors, right, when they are off. Those capacitors rings with the leakage inductance of the transformer and, creates trouble, right? So these problems are there. Still we all like PWM converters. So till today, in my understanding, 90 to 95% usage of isolated high power DC-DC converters are full bridge converters, right? But now we have also two other very interesting alternatives are there. One is LLC, it's a resonant based converter. It has also become very popular. And then also you have dual active bridge. Now the Chinese people like dual active bridge a lot. All their product, they're trying to put dual active bridge. Americans like LLC because they've silly invented that or whatever, right? But still in the industry or wherever you go, there is a lot of discussion, right? Which one is better? Is it really better than, phase shifted full bridge and all that, right? So what I'm going to do is, we have actually designed the DC-DC converter that, because phase shifted full bridge story I don't want to tell you, it is there in the textbook. So what I'll do is I will today discuss dual active bridge and a design with dual active bridge. It is a bit fancy today. And then if there is time tomorrow, I will also little bit touch upon on LLC, right? From a EV design perspective, right? Again, the flow is same. First, I tell you the topology, then I will tell you how that works, and then and closed loop, right? And then once we finish all that, we go to the design, right? So I don't know how many slides you get. Where is Bharat? 12 slides. No, I told them to make some slides. Let me see if it's there. Oh, it's there. Some things are there. Okay. Okay. So by the way, I should tell you that all this work is done by few of my students, and a lot of them have helped. So one of them is, his name is not there here, but he's there. Shobi Broto, then Shayan, these are two my senior PhD students. Without them, this project would not have happened, and also Bharat and Malingu. They are just two BTech students from NIE, but very bright. Because of them, this project has happened. And of course, others have helped. So, okay, DC-DC, right? So DC-DC, already we got the 400 volt, and somebody is controlling, the PFC is controlling the DC-DC, so it is fixed in our problem. But the output voltage, the 48 volt, that is nominal, but that 48 volt, as the battery charges, discharges, it changes. So typically, you know, you will have some graph like this, I think all of us have seen. So when the battery is at lowest voltage, we are talking about charging here, not discharging. So battery, when it's lowest voltage, you pump constant current, this is called VCC. And then once the battery voltage reaches top voltage, this is called VCC voltage, right? So then what you do is you stop, you try to maintain the voltage, don't regulate the current anymore. You maintain the voltage, and whatever battery takes that current, that takes, but of course that current will be lower than this current, and this is called trickle charging, right? So this particular project, the thing is that here, this voltage is 55 volt maximum. This voltage is how much? 40 volts. This voltage is 40 volts, and this current here, the maximum current, not this one is 55 ampere, right? That is that. So if you actually multiply 55 into 55, you will get somewhere around some 3 point some kilowatts, right? So this is the dual active bridge, but any of this has the same structure. So there is a bridge here. That bridge generates a high frequency AC. That AC is passed through this transformer, and this guy sort of rectifies it, and then gives you a DC voltage here, right? But unlike phase shifted full bridge, what we have here is, we have actually an inductor here. Now this is not the leakage inductance of the transformer. Leakage inductance of the transformer may help that, but if somebody is telling you that, no, it is the phase shifted full bridge, we just use the leakage inductance of the transformer, it will work like a dual active bridge, is not true. Because this inductance is quite large, it cannot be just leakage inductance, and this inductance has to be also controlled precisely. Leakage inductance cannot be controlled precisely in order to do all the power flow, all these things to work, right? So actually there is an inductor. Now because there is an inductor here, right, there is a voltage which can switch to this inductor, and this inductor is switching through this. If you take the transformer almost ideal, right, then this side you cannot put another inductor, because what is coming here is a switching current, right? So that's why you have to put a capacitor, and you can put another inductor here. So all the switching ripple will go through the capacitor, and then this is basically the low pass filter, right? In phase shifted full bridge, you get a pulsating voltage here. So you put like buck, LC you put, right? But here it is switching current, so you put CL, right? A lot of people don't put this L, because this L may be enough, the wiring inductance may be enough, but this capacitance is needed. So some people will say that, you know, here the big advantage, right? There is no inductor here. This inductor is a switching frequency inductor, high frequency it will be, but there is no inductor here. But inductor is not there, but there is a huge capacitor here. This capacitor is quite big because it is going to see a huge switching current. Remember, the capacitance seen by boost converters are much higher compared to the capacitance seen by buck converters, because buck converter actually it is flat current with some ripple on it, but in boost converter it is actually switching current flowing, right? So it is like that. So now what we will do is we will try to understand how does it work, right? So you have seen that there are 8 switches. So if I tell you how to work with, we need to understand how all the 8 switches I'm going to switch to do the job. And what is the job here? The job here either to control this voltage or to control this current, right? That is the job. Or in essence, control this power, right? Okay, so now actually if you look at here, see through this bridge, right, I can apply V1 here, I can apply minus V1 here, I can apply 0 here, right? So when I turn on this two, it will be V1, when I turn on this two, it will be minus V1, when I turn on either the top two or the bottom two, it is 0, right? So essentially with this bridge, I can actually apply a quasi square wave, correct, which has got 3 levels, plus, 0 and minus. Same thing is true here, right? Same thing is true here. And transformer, you can actually reflect everything on one side, right? Let's say we reflect everything on this side, right? And then if the transformer is ideal, let us don't take the magnetizing inductance, then the transformer can be replaced with just the leakage inductances, and those can add in series to this inductor, right? So what we have, so this is the equivalent circuit. So equivalent circuit is very simple. There is an inductor and there are 2 sides, I have 2 switching sources in this, right? This is the picture here, correct? And now if you look at the primary voltage, what I will do is, this black is the primary voltage over 1 cycle. It's a square wave I am applying. So right now, okay, I will discuss with square wave, I will tell you this. So what I do, no, we do also some kind of a parameterization here. Say for example, this V1 voltage is 400 volt, right, in this problem, right? But what I am drawing is, I will take a base voltage which is V1. Okay, so then this waveform will be 1 and minus 1, right? In that parameterized base, like we have done this parameterization in our power system, right? So if you do parameterization, lot of things becomes very simplified, and then you can quickly go from design. And because if you can do parameterization, you can also talk about a dual active bridge which is between 48 volt and 12 volt, and also 400 volt and 48 volt, right? So that is the advantage of parameterization, right? So you get this, and then you know this is basically the reflected voltage from that secondary bridge, which is n times that, 1:n is the turns ratio, right? N times of that. And here what we have done is, we are defining M as the reflected voltage NV2. Remember this side it is 48 volt, right? This is 48 volt, right? This is 48 volt. So this is the reflected 48 volt divided by 400 volt, right? That is what I am calling M. So M is actually turns ratio, representative of the turns ratio of this inductor, of this transformer, right? It is switching, man. This is actually VP and VS. I mean, we have taken that is the plus and this is the minus. It is not DC. It is switching. Polarity is that how we defined it, right? So what we are doing is, now you can actually apply a square wave or you can apply a quasi square wave, right? A square wave with duty cycles. But so if you apply square wave with duty cycles, you got 2 quasi square wave with 2 duty cycles, this black and blue curve, right? And also you can do a phase shift between them. So there are actually 3 control variables, right? 3 degrees of freedom. The phase shift between these 2 square waves and the duty cycle of these 2 square waves. So this is what we call triple phase shift, which is little bit advanced, and that I am not going to discuss today. But whatever the design we will discuss, that comes out to be almost similar if you take all these complex things, right? So that is why today what we will discuss is, both the bridges are applying square wave, but with a duty cycle, with a phase shift, right? So see this black one is applied by primary bridge and the blue one is applied by the secondary bridge, right? And then what we have done here is also we have the time, right? That also we have parameterized. So there is a switching frequency here, maybe 100 kilohertz. Actually what we are doing is 250 kilohertz in this case because it's off switch. I think we can do up to half a megahertz. That is possible that we are working right now. So the thing is that that also you can parameterize, so that I will call this as pi and this is 2 pi, right? So the blue one is actually the applied by the secondary and reflected. So that has these levels m and minus m. That is 48 into turns ratio divided by 400, right? So if you actually see this, right, this is the waveform and this is the waveform and this is the phase shift between them, right? And that is what we are calling pi delta by 2 in this. So why we have a pi here because we want delta to go between 0 and 1, that's why, right? So basically when delta is 0, both of them are on same phase, right? And when delta is equal to 2, then you can see that these just out of phase in this picture, right? And interestingly, this equation, right, it is basically Vp minus Vs prime is LDI dt, right? Nothing is there in that, right? That is the equation. So actually if we parameterize this, right, with this base, so we take the 400 volt is as a base and also we take 2 pi FSL of this Z base, right? See, in a circuit if you have to parameterize, you need a voltage or current or impedance. One of them if you get, the other one you got, right? And also you need frequency base. So that is what we are doing here, right? So frequency base we have taken as a switching frequency of this converter, right? So then what happens is the equation becomes simple like this. Now people actually can do all this without parameterization, no problem, you will get all the result. But the thing is that you may not get much insight if you do that, right? Okay, 5 minutes will go, I'll just explain this and then maybe the design we will see tomorrow. Okay. So then what is happening is that you are actually, this is the equation, right? So here is a square wave, here is a square wave with m as its magnitude and then this is d theta of this, right? So obviously these are all, so if you look at the actual voltage applied across this, that is black minus blue, which is like this, right? All of you can see that, right? So when this is negative, this is actually, it is minus m, this is 1, this is actually 1 plus m. This is 1 minus m, it is minus of 1 plus m and this is minus m. Everybody is following, right? That's all, right? It's very easy. So now the thing is that this is the green waveform is what we are applying across the inductor, right? So then what happens if you apply a DC to an inductor? The current will be a ramp, right? So that is how the current looks like actually, right? The slope of the current depends upon these levels, right? So here the slope is high, this is high, so slope is high. Here this is low, slope is low. When it becomes negative, it will start reducing, right? So essentially all I am trying to say is that the current in this converter is going to be linear and with some slope. It's like a triangular current, but not really a triangle, right? But linear, something like that, right? So that is what first thing I'm saying. And then what I'm saying is that look, this m has this level 1, 0, minus 1, 0 we are not using, and this guy has levels m and minus m, right? And your time is the theta, which is only has this delta as a parameter. Everything that you compute will become a function of m and delta here, right? Where delta is your control, your duty cycle, and m is your turns ratio, right? And everything else, everything is parameterized, right? So now what you would like to do actually here, right? So the idea is what we are going to do is we are actually say controlling the power. You always know what is the power that needs to be fed from that VCV characteristics, right? So if you look at the power, so this is actually very similar to the power system business, right? You have got two voltages and you have got a inductive impedance in between. You phase shift between them, then P becomes what? Some V1, V2 by 2 pi FL sine delta, right? So here, because this is like that, you don't get sine delta, but you get some function of delta, right? So you get that. So this is what you get, the power. This is again parameterized power, and you can see the form is very similar. There is M here, 1 here, pi is coming because of some calculation, and that x, V1, V2 by x, right, in your power system, that x is not coming because I have parameterized. I have thrown the L out. So if you multiply this with the power base, then L will come back to this, right? So the thing is, but this guy, instead of delta, it is actually sine delta, it is here delta into 2 minus delta, right? So actually if you plot here, this is the power, and that is how it looks like, exactly like sinusoid, but it is not actually sinusoid, it's a quadratic curve, right? And also like sinusoid, you have this point. So interestingly, you can see that maximum power that can flow here is this point, and this is delta equal to 1 is where you get the maximum. You can differentiate and see this, right? You get the maximum, and that maximum is m pi by 4. V1, V2 by x, that is the maximum, right, in power system, right? And like the power system, for the same power flow, you have 2 delta angle, right? For the same power flow, you have 2 delta angle, but in power system, you don't operate at this delta angle. You know why? It is unstable, right? And also the current will be high on that side. So same thing happens here. Here also you have 2 solutions for delta, will transfer the same power, but if you transfer at delta higher than 1, you are going to get more RMS current that you don't want. So that's why we restrict delta between 0 and 1, right? So now control, right? So in the control, 5 minutes, started 4:15. 5 will help plus, okay, 5 minutes. So the thing is that here, the job of this converter, what is the job of this converter as a DC-DC converter? You have to control this voltage, right? You have to control that voltage. So what is here? Here also like the same picture, across this capacitor, this side is the load, whatever the battery needs to be pushed, right? And this side is the power, this power, right? So if I put a voltage controller, the voltage controller will tell me how much power to push, right? If I am controlling this voltage, whatever you have to give it to the battery, right? You will, if say you are in CV mode, right? You are controlling the voltage, right? So to control the voltage here, whatever the battery is drawing, you have to give, correct? So that how much is coming into this will come from your closed loop, right? So you take the feedback of the outer voltage, compare it with 48 volt, wherever you want to maintain, or you are now at 55 volt or whatever. You compare that, give it to the controller, controller will tell you the power, right? And then once you know the power, you can just, calculate delta. This is this equation only, I have just written in the other way. You can calculate delta and give that delta to your converter. There are no other control here, right? One square wave from the primary, another square wave from the secondary, only control is the phase shift. So if I have to maintain the voltage, how to get the phase shift is I am telling you. How to get the phase shift is this way. You can also do the current control, where this current and this current as well, but ultimately it boils down to a power, right? The same thing can be written when you are in the CC mode, right? So now the thing is that what happens here is that we also want GVS. So I think I'm just done with this. So the GVS is that actually if you actually look at this current waveform, right? So by the way, how I got the power? I got the power by solving this equation. I know the voltage, then I can solve this equation and I can find current. And once I can find current, I can multiply with the voltage and I can find out power. This is the average power over that cycle. It is just the assignment problem, right? If you do that, you will get it, right? Nothing is there in that. So, but here to solve this problem, solve this equation, right? I have given you the voltage, but is the voltage enough for you to find out this current? Anyone? This is a differential equation, right? This is the simplest differential equation in the world, right? dx dt equal to constant or something, right? So what is that is still needed to solve this? Someone said, I think, not duty cycle. Say duty cycle I know here. Say delta I know this waveform. The green I know. The impedance is buried in this. No, I have this equation now. But I need something else right here. Yeah, I need the initial condition, right? Without initial condition, I cannot solve this. But what I am going to tell you is that, okay, you can solve, you assume some initial condition, and you solve this, right? Once I assume an initial condition, now I can find out in terms of that initial condition. But then what I will tell you that we are talking about steady state, right? So once this cycle is over and it starts repeating, wherever I started here, I should come back there. This should not be -1, this should be I1 again. I think some mistake is there here also. We can correct it, right? So you should come back to this point. So actually if you use this condition of steady state, you can find out your initial condition and you can solve. You will get that equation, right? And then you know your power, you know as a function. But now I also want soft switching, right? Then only I can increase the switching frequency. Now here, soft switching, to get soft switching, what has to happen is, I think I have not shown you here. So see, so when the switching is, say for example, this switch is conducting, right? And the current is flowing through this, right? So now what happens is that I can actually make this as a current sink because the switching is happening much faster than those currents changing. The switching is happening somewhere here or here, right? It's happening much faster. So I am looking at that switching instant. So that switching instant, I can think that this is like a current sink, right? Its current is fixed, it is not changing, right? So now what happens is that if the current is in this direction, so what you are going to do if you are changing the switch, so you are going to turn this guy off, right? And the moment you turn this guy off, then the current will transfer to this diode, right? And there will be a hard turn off. But then you will turn on this guy, but this guy when you turn on, right, already this diode is conducting. So there is no loss in this turn on. Now it turns out that in case of this kind of MOSFET, silicon carbide or gallium nitride and all that, this turn off loss is very small, right? This turn off loss is very small, so I would not worry about it. I have to always make sure that the current direction is such that the guy who is turning on at soft. Its diode should come off first. But here I am telling you the other case, right, where it is, so we want this case, when you are going from top to bottom. We want the current to be in this direction. Let us just see, we are in top to bottom, but the current is in this direction. Then what will happen? The diode is conducting, right? Here the diode is conducting, not the switch. So maybe you have the switch on, maybe the reverse channel is conducting. The moment the switch turns off, first you have to turn off this guy, so the current will go to the diode. Now you are going to wait to turn on this guy. That is a dead time. So when you turn on this guy, now the diode to switch, it is going to be a hard turn on, and that will be lossy. So the fundamental thing about soft switching is, when you are going from top to bottom, your current should be in this direction. And symmetrically, when you are going from bottom to top, the current should flip. Correct? So this is called direction based GVS, zero voltage switching condition, right? So the thing is that here, if you actually think, this is when the the primary is switching. So to get soft switching, I want this current to be negative. And when you are switching the blue, that is this point, I want this current to be positive. It will come out from that discussion. That you know the bridge is switching, so if you look carefully, you will see that, right? But it is not necessary that it will be always like that. I have just drawn this picture. So there is a condition. So if you look here, this I1 and I2 I can now compute, no? Remember, I can compute all that waveform. So if you compute, you will find out that I1, I2, those instant currents, right? They are functions of M and delta. M is your turns ratio here, and delta is your control here, right? So this depends upon this, right? So the thing is, if you want the correct directions, right, then you have to have this condition satisfied, right? So now what we do is through control and design, because I can design this, I still have to choose what is my turns ratio, what is my inductor value. So that is the design here. So I have to do the design such that I should get always soft switching, right? I should always satisfy this condition. And also another thing is that I have this RMS current, right? The current has this RMS because it is going that, and that results into conduction loss. I also want to make that current minimum, so that the conduction loss is minimized. Now here, if I am doing only phase shift control, I am not doing the triple phase shift or duty cycle control, I have only 1 degree of freedom, delta. So with delta, I can control only the output voltage. I cannot reduce the RMS current. So if you are doing this kind of control, which is the baseline control, then the only way to minimize your currents is through design, because remember, all these currents, they depend upon also the inductor value and also the turns ratio. And also the RMS current is a function of inductor value and turns ratio, right? So that is why I am just writing this, and we are going to see, this. So we understood the operation of dual active bridge, and we understood that how this N, L, they are actually through M and delta, they are connected to this. And then we will give you a design like I did for AC/DC. So maybe we will do that tomorrow and show you, how we have chosen and all that, how we have made this converter. Here also we are using gallium nitride in both sides. Primary side we are using the same GaN system, 650 volt. Secondary side we are using EPC GaN, 100 volts, right? I think it's enough, 2 hours. So we'll stop here. If we find some time tomorrow, we will discuss LLC and we will discuss little bit of drive. So we are talking about the DC-DC, right? It's a practical example case of two-wheeler, right? Fast charger for the two-wheeler. We have seen how to get that 400 volt DC from the single phase AC, right? And then you have this isolated DC-DC, and then you have to have, this side is the battery, and you need a galvanic isolation for safety and some other reason. And what happens is that, I think you heard about this a lot today, about this charging profile of the battery. So what happens is that initially you try to pump as much current is possible, and this is called the constant current region. So voltage goes, this is the discharge battery. So in this case, the specification was that it will go down to 40 volts, and then we sort of pump the current and push the voltage up to 55 volt. And so till that point it is current control, and once the voltage reaches 55, then you stop doing current control and try to just control the voltage, and the battery will take whatever current is needed to maintain that voltage, right? So that's essentially the constant voltage region. So we need a DC to DC converter to do this. So, and also you can see here, this is 400 and this is 48, so a high drop. So we need to use a transformer, and because the power rating here, actually if you multiply 55 into 55 here, it is a little more than 3 kilowatt. So we cannot use something like flyback, we have to use a full bridge kind of topology. And then we said that, one of the interesting thing that is now better than PSFB, phase shifted full bridge, widely used phase shifted full bridge, is this dual active bridge converter. And basically what is happening is that you have, of course, both the side you have 2 H bridges, and in between you have this high frequency transformer. So all you have to do is you actually generate a square wave here in this bridge, and also generate a square wave here from this bridge, and then what you do, sort of phase shift them to do the power flow. And if you consider the transformer to be ideal, there is a series inductor here. If you consider the transformer to be ideal, then it is essentially the picture is two voltage sources connected across an inductor, right? This is the very well-known, our power system picture, two sources, AC sources connected through an inductor, and we know that, if you phase shift, there is a power flow, and it is very similar here. Instead of sine, we are using square wave. That is the difference, right? So of course you can do, this waveforms. You can also have quasi AC. You can have duty cycle control, and that is what is called the advanced TPS control, triple phase shift control. But we are not discussing this today here. Our designs are based on that. But the thing is that interesting thing is that the actual design, the baseline design that I'm going to talk to you about here is very similar even if you take TPS modulation in it. Okay. So the thing is that, and then once we said that, what we do is this kind of analysis, it is better to be done in per unit, because if you do it in per unit, I can talk about a general specification, right, general thing, and then, tomorrow this battery may not be 48 volt, it could be 400, you may have a 800 volt bus for bus or truck, right. I think some L&T guys are here, they are doing 800 volt to 400 volt, and then they are using a 3-phase DAB there. So, but the thing is, this per unit analysis is strong, powerful enough to take care of all that. Specification doesn't come into picture, and I can tell you the general essence of the design, right? So, so what we did is, we said, okay, we will per unitize, and in an electrical circuit, you need 3 base quantities to per unitize everything. So what we have taken the voltage here, that is the 400 volt on this side, which is not changing. And then if you do that, the primary applied voltage becomes this black waveform with unity 1 and minus 1. And then you take the reflected secondary voltage, that is the reflected 48 volt, V2 is that 48 volt, and then you reflect it and use the same 400 volt base. And then what you get is what we are calling here M. So M is nothing but the turns ratio. For you to understand, M is the turns ratio, but for a given turns ratio, when the battery voltage is going to change, M is also going to change. That's what we are going to see, right? So, so that is your M, and then you are taking the, so Fs is the switching frequency at which we are generating the square waves, right? And then this is your impedance base. So once you have this two, and also we are taking this frequencies as the time base, switching frequency as this time base. So when I say the time is 2 pi, that means it is 1 period Ts, right, in actual time. This could be, 100 kilohertz or something like that, or in this particular design, it is a quarter of megahertz, right. So anyway, so we discussed that, and then what happens is that if you actually parameterize, this equation also becomes very simple. And then you just see that you have dd theta, and this so that is this green waveform, right? So it's just inductor fed by a stepped voltage waveform. So the currents are going to be triangular. It will be straight line currents like what you see here. And the interesting thing is, if you see that this square wave is 1 and minus 1, and this blue square wave is m and minus m. And then, the phase shift we are talking about, it is in terms of delta. So it is pi by 2 delta, that is what this in theta, that is this shift. So that means you can see that when we come, delta is 0, the angle is 0, then basically blue and black will coincide. And then when delta is essentially 2, that time what is going to happen is that you are going to get a 180-degree phase shift between these two, right? It will become pi, this point will move here. So that is the scaling. So, and delta is your control variable. You cannot, so here in this problem right now, the idea is that you don't have any control over these voltage levels. They are given. You are just making to square wave and phase shifting them. By phase shifting, you are controlling the power flow. And the power flow is what needs to be controlled. So, from this perspective, if you see that actually what happens is that, because it is 1, m and delta, only these 3 parameters are there in the equation. And then I said that, what happens is that if you can solve this equation, but you need an initial condition. But the thing is that we are considering steady state. I think some of these things are corrected now. So steady state. So the thing is that this green waveform, when it comes back and goes to this point after one period, right? This point should be same as this point because things have reached steady state. It is periodic, so it's every cycle is identical. So the thing is that if we know that, we can actually now find out exactly this current waveform. And as you can understand, this current waveform will be in the per unit a function of m and delta because that is the only two parameter here, right? So that's also clear. And then once I find out the current waveform, then I can multiply that with the voltage from any one port because inductor is not taking any power. I can multiply it from any port and I can calculate the power. And then that will be instantaneous power, something, it will not be steady because your voltage and current both are changing with time, but you can take the average power, right? And you can see actually the voltage and current, they have half wave symmetry. So it's like the on the other side of the rectifier. So, the power remains same. Even though they multiply, the negative voltage multiplies with negative current and power remains same, right? So that's the thing. So given this analysis, what I'm all saying that the power and all the current, everything you can compute in terms of m and delta, right? So that is that next picture. So what we have said that the power P, if you do the math, right, you will get this as a function, and it is it is very similar. It looks like that V1 V2 by 2 pi FSL sine delta. So you are not seeing the L because I have prioritized it. That is why you are not seeing it here. And M is the turns ratio. It is coming because those two voltages are there. And this is this function, and interestingly this function also looks like that inverted sine, and there are two operating points like in power system, and we would like to operate here the delta lower than 1 because here stability is not the problem, but the problem is the current will be high even though you supply the same power, because we also calculate the RMS current. You have the triangular waveform, you can compute the RMS of that waveform, and that is the function, right? So the thing is that what happens is that you are sending out same amount of power for delta 1, delta 2, but if you are doing at delta 2, then this current is going to be high. It is possible to show, and that is why we will keep our phase shift limited to 1, 0 to 1. So that means in angle it is pi by 2. So I will not go beyond pi by 2, same as what happens in the delta angle in power system. I don't go beyond 90 degree because then I will go in the unstable region. So the thing is that now if I view this converter, like we are all talking about power and all that, but if I view this converter, actually there is a load here, this is the source here. The load here could be the battery and like that, but it could be also a resistance or anything like that, where you want to supply some load. So essentially the load is essentially the voltage into the current that is drawing, right? The P naught into V naught is the, I naught into V naught is V naught. So actually, if you actually, you are drawing some current I naught, if I have to maintain this voltage across this capacitor to say V naught, then I should draw a power that is V naught into I naught, right? So that is essentially the thing. So the thing is that if you want to maintain the voltage here, so basically the model is this, that this is like same as what we have seen in the rectifier case. No? The output of the rectifier, we are drawing the power from AC, and then that side you had a sink who is taking the power. That was the DC-DC, this guy, right? So essentially what happens here that you want to control this voltage here. You can also control the current, but say you are controlling this voltage, then you have this outer voltage loop. You want to maintain the voltage to VCV maybe, and then you feed back that voltage, you compute the error output will tell you what should be the power, or you can also compute what should be the current. It's the same thing, right? What should be the power, and the moment you know what is the power, you can actually calculate delta. Given you have the knowledge of M, because you are sensing the voltages, you know what is M based on the turns ratio, and then you can find out delta, and then you can apply it, right? So this is, I think, the point we came last time, that in a dual active bridge, how I make the DC-DC, right? What is the closed loop control and what is the switching strategy? So both of them are clear. So if I give you now dual active bridge, designed dual active bridge, or in a simulation you know how to use it, how to work with it, how to flow power. If I ask you that, okay, why don't you control the voltage here to 48 or 55 volt, right? You know how to do that. Or if I tell you, which I am not showing here, that if I tell you, no, you make sure that the current is 55 ampere, right? So then what will happen here, you will have a current control loop. I will not control the current. I am going to control the current. That current control loop will tell me what is the power, right? And voltage will appear accordingly, according to the battery characteristics, right? So the same thing will work, and you know how to do that, right? And then we talked about also the zero voltage switching, because that is very important, and that is how where we can, we can cut down on our switching loss. And we have seen before, switching loss is connected to the switching frequency. So if I can disconnect the switching frequency from switching loss, I can increase switching frequency. And if I can increase switching frequency, my sizes go down, right? That's the basic fundamental idea. And then I told you here that, this 8 switches, right? So if you look at the bridge actually switches, the primary bridge switches at this point when the value of the current is I1, this current is I1, and the secondary switch switches here when the current value of the current is I2, and because of the complete symmetry here it should be just minus I1, it's a mirror, right, because of the steady state and symmetry, and this will be minus I2. So if I just worry about these two, automatically these two are satisfied on that square wave because of the symmetry. So I need to only satisfy, make sure that this and these currents, the instantaneous currents at those points, has the proper direction, right? Yesterday I talked about that when you are switching in a particular leg, there are 2 switches connected in series, right? So when you actually switch, what you do is you turn off one device, and with a dead time you turn on the other device, right? So now if the current is actually flowing through the switch, the moment you turn off the switch, it will move to the bottom diode, and switching will happen at that instant. So when you turn on the other switch, already the diode is conducting, right? But if when you are doing the switching, if the current is actually flowing through the diode and not the switch, right, then if you turn off the switch, still that diode is conducting, and when you turn on the other switch, then there will be a hard turn on for the other switch. Now the turn off losses, I told you, generally for gallium nitride or silicon carbide devices are very small, unlike IGBT, right? But turn on losses are very high. So the whole point is, in these converters, what we would like to do is we would like to avoid hard turn on. Right? That is the fundamental point. So that is why we want to make sure that, this current, and if you look at the direction, if you again look at this circuit carefully, this current should be always negative, and this current should always be positive, right? How that comes, you have to just look at the circuit carefully, and then how I told you switch to diode should happen, that will. If somehow this current becomes positive, it is going to become a hard turn on that bridge, on that leg, on that instant, right? We don't want that. Now, if this converter is already designed and given to you, you have no control over soft switching or RMS current, because customer or the loop will tell you what power to be pumped, voltage or current, anything they will tell you, and that will immediately decide what your delta is. It is same as like a buck converter. You don't have any other control. Whatever customer wants, you have to set your duty cycle, closed loop control to that to get that output voltage, correct? It is like that here. So only thing that we can play with in this is to minimize the losses and ensure that, GVS happens in all this operating condition is through the design, right? Through the design. So because my operating point, there are, infinite number of operating points here, right? Here when the voltage is rising, current is fixed, and here the opposite, right? So what we are going to do is, now in the design we have actually 2 variables, 2 things to design actually. One is that what should be the value of that inductor, what should be the value of that series inductor, and second thing is what is the turns ratio of that transformer, right? These are the 2 things I have to decide. Once I decide that, then for all operating point I know what is the RM, because you know the operation. you can exactly calculate what will be the RMS current, what is the maximum RMS current, what will be the volt seconds and all that. You can design the transformer, you can design the inductor, you can choose the devices. And in the devices now, remember, if we can make sure that GVS happens, I don't have to do that complicated switching loss calculation in this case. I have to just do the conduction loss calculation. So actually, if you know the RMS current, and that you will with this formula, right, you can simply compute what will be the drops in the devices. And remember, always in every bridge, two devices are conducting. So there is one RDS on, another RDS on. So it is basically I square RMS into 2 RDS on in each of the bridges, right? Easy to compute the loss, right? And then you can figure out whether, you know, depending upon which one gives you smallest RDS on. There is also the RJC is there, which is connected to your temperature and all that. So you know already, I have already told you how to select devices. Same way you can select devices for these guys, right? But the main question is, how can I find out that turns ratio N and the inductance value L? So that is what we are going to do. And what we are going to do is, look, we are going to say this. This may be a little bit complicated. If you just don't understand, no problem. You can take the formula. Formula means you can take the design. I will try to give you the logic. If you don't understand, no worries. It is a little bit more complex. But idea is that one thing that I would like to do in this converter, right? I would like to design this and this, and you know the input voltage and the output voltage and output current are going to change like this, right? That will change the RMS current here in this converter as you move on that operating point. Say I have already designed. Now based on the value of L and N, and those two voltages, battery voltage is going to change, current is going to change, power is going to change, and you are going to see different operating point, different RMS current. So one thing that we would like to do, we would like to make sure over that entire operating region, the RMS current, the maximum RMS current is minimized. I will choose that N and L so that the worst case RMS current seen by this converter is minimum. That will make your transformer small, inductor small, your the switch rating smaller, right? Because there is no switching loss here as per se. It is all conduction loss here. And always this inductor, these switches and the transformer, they are all carrying this current, correct? So now it is possible to show actually over these operating points, right? This is the point actually the power is maximum. You can see that because that power is the product of voltage and current, and this is the point the power is the maximum, and it turns out that this is the point at which the RMS current also become maximum for the same value of N and L for a given design. For a given design, you go over this operating point, your RMS current keeps changing, but turns out that this is the point where the RMS current becomes maximum. So now what I will do is I will not look at the RMS current at any other point. I will just look at this point and will try to choose an N and L value that makes this RMS current minimum, correct? So that is my strategy. And also I want to ensure that GVS happens in all these points. That is also I want it to happen, right? Because that then only your conduction, your switching losses are minimum and you are at a highest efficiency, right? So what we do here is, so see, if you can ignore this math if you think this is too much, but I will tell you basically what is happening. Look, everything in power unit I have computed in terms of M and delta, correct? But actually in the operation what will happen is I will get to flow a power P, right? And that P will tell me what delta is, this equation, right? So essentially M and P decides everything because M and P together decides what delta is going to be. So actually all this RMS current I can write in terms of, rather than M and delta, I can write that in terms of M and P, okay? And actually what will happen is, ignore the star, if you do the math, right? P naught is actually that point, VCV into ICC, that peak point, right? We are looking at that peak point and that power is P naught, right? So if you look at this equation, M is by definition is N VCV by V1. V1 is 400 volts. V1 is 400 volts. VCV is that 55 volts, right? So M is nothing but N multiplied by this constant, right? So M is same as N, okay. And also if you do the math, you will see that this small p, the per unit power, small p at that point is a function of P naught by V1 square. This P naught is that 55 into 55, that maximum power, divided by 400 square into 2 pi FSL. Fs is that 100 kilohertz or whatever, right? That switching frequency into L. So this small p is actually L and small m is actually N. So if I can, so I am trying to do an optimization on N and L, but N and L optimization is same as optimization on M and P because they are same, right? So if you actually do that, so that is what we are saying. So if you actually do that, and we are looking at the RMS current, and now look, the RMS current in the primary and secondary, you may say they are actually same because they are just multiplied by the turns ratio. But I have not yet chosen the turns ratio. Turns ratio is still I am considering in my design, right, in my optimization. So what I do is I fix a particular N or M and look at what is happening to my RMS current. So this blue is the primary RMS current and red is the secondary RMS current. For a given value of M, I am optimizing on P or L and finding this out. And this is that optimized. So you are asking this question, for a given value of M, what is that P so that RMS, primary and secondary RMS currents are minimum. And this is that graph. Say for example, if you take M equal to 0.5, this P value is somewhere around 0.37 or something. And that is the value of the RMS currents, right? So now interestingly, if you look at this, now I can sweep the M over some possibility, whether it will half to 1.5 or 2, right? And you can clearly see that M equal to 1 is the point at which both of them comes here minimum, right? At least mathematically that is what we are going to see. And M equal to 1 means it is just the turns ratio. So the turns ratio is basically, it is telling should be 55 by 400. It is telling turns ratio is 55 by 400, right? So that is, if you don't understand also the math, that is the message. As a design engineer, that is what you can try. Start. Go ahead.
Just a comment.
Yes.
Without doing the math, I was just thinking.
Yes.
Say if your turn ratio was high, that means you would have a large voltage on the secondary side being developed.
Right.
Or if you want to think of it across the inductor, right?
Correct.
And you would have too big a voltage.
Mm-hmm.
Therefore, you would have more power than necessary at full.
Circulating power. Correct. Correct. Correct.
But if
Correct.
your turn ratio was too small, that means your
It will be other side. Other side would be correct. 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 Intuitively, you can see that it should come very close to 1. Actually, what happens is you have two voltage sources and you are trying to transfer power. What is the best? No inductor, just the turns ratio you do, short it. Correct? That is the best thing, and that is what it is telling. It is telling P equal to 0 at M equal to 1. So what is P equal to 0? P equal to 0 means L equal to 0. So it is basically telling, you have 55 volt here, you have 400 volt here, match the turns ratio, connect them in parallel, you will transmit the best. There is no loss, no, nothing, right? That is the intuitive point. Exactly, you are absolutely right. But we cannot put L equal to 0, right? Actually, then what happens, everything becomes 0 at that point, right? So that is why what we are doing is, we are suggesting that, at that point, so at 48 by 400, 55 by 400, that is the point you do the turns ratio. You choose that turns ratio equal to such that it is for 55 by 400. And then don't choose L, because if you choose L like that, L will come to 0, right? Because that is what the optimization is giving. We cannot do that. So at the highest volt, so then now we know the range of M. Look, M, see M is output voltage by input voltage turns ratio, correct? So the thing is M becomes 1 when you are at 55 volt. So M becomes minimum when you are at the minimum voltage, right? That is 40 volts. So you are going to go between 1 to when this is 40 volts, right? So essentially, if you do the math, it will become that VCB. So it will become 40 by 55. So that is the M you are going to go down, right? So now we are asking this question. Now people do it differently. See, L we have not yet chosen, right? So one thing you can say that, okay, you know, in this converter, I am not going to look at GVS, but I am going to say, you know, I should get the maximum power. I am going to flow the maximum power through this, right? So my maximum power is that point, 55 into 55, right? I put that power here, and then that point M is equal to 1, and then immediately from this equation you will get the value of L, right? It is like same thing. If I say that I am going to, there is a maximum value of L, a possible value of L, which will let you run delta in the entire region, right? Some people will say, no, I will choose a lower delta, right? But if you choose a lower delta, your operating range is reducing. See, instead of this as that 3.2 kilowatt, you are calling this as 3.2 kilowatt, right? So another way to look at this, so now there are a lot of variations are possible and all that, research is there, people are working and all that, and I also talked to you about the direction based GVS. But actually what you have to have is magnitude based GVS. I cannot go into that detail, right? This is a short time. So, but I may say that, well, you know what, for all other value of M and all other operating point, right, I want soft switching to happen. So now, you know, I can actually, I did calculate this, right? I can also replace deltas with P in this equation, right? And then I can see pi by 2 is okay, you can neglect because it is with 0, right? So actually you get these two equation, right? So now what is going to happen is, look, now as I'm going to change here, right, your aim is going to change, because as the voltage goes below to 40, your aim is going to change, right? And if your power is also changing, your delta is also going to change at all other operating points. So what you have to do, choose the value of L such that for all the variation of delta and M over the operating range, this is satisfied. Not P min, for all power. For all power. See, this is not like that PSFB that is lower power. See, even if you are not flowing any power, you are going to see a current flowing, triangular current flowing, circulating. But if your aim is equal to 1 and you phase shift to 0, there will be nothing, right? They will cancel each other. So what you can do is, so now look at one condition is delta is greater than 1 minus 1 by M. But the way I have chosen M is less than equal to 1, right? My maximum M equal to 1 at the 55 volt, right? So M is always less than 1 in this design, the way I am choosing it. So this will be always satisfied, because this guy is always less than this and it is okay. But what about this thing, right? This may not be satisfied for all point, we need to see. See, now the thing is that I have this, so you are looking at any general point in your operating condition where M is going to change, delta is going to change, right? M will change based on the output voltage variation, delta is going to change based on M and also what is the power that you are drawing, right? So what you can do is, already we have calculated P in terms of delta, so I can replace this with P, right? And replace with that with P, and then P I have this expression, I can replace that with L, and then I can also replace that with M also, can we replace that with output voltage and this, right? So if you do that, see, this is just a math, there is nothing there in that, right? If you do that, you will find out that L should be greater than this number, right? So this is just some calculations, one of the way. Design, there is 1,000 ways of doing one design. I am telling you one baseline design, and this design turns out to be very close to the optimal design, considering TPS, phase shift and all other things, direction based GVS and all that, right? So I think you understood, right? What is it, right? How we are doing it, how we are going to do the design, right? Okay. So you guys have to get tea, so I have to quickly finish. So now the thing is that we had all these specifications, right? We have this, and then I told you how to compute this. So that's how we computed L and all that. So and we know what is the maximum RMS current. So once you know the maximum RMS current and the value of the inductor, you can design the inductor, you can design the transformer, you can design all of that, right? You can choose the devices, calculate the losses and all that. So that is what is being done. So primary we are using the same devices, but here instead of 60 ampere we are using 30 ampere device, and the first design we considered 250 kilohertz, but now because GBS is happening and we are happy, I think next iteration we are going to go to half a megahertz and it will become very small. Some of you have seen in the lab, right, the dual active bridge yesterday. Some of you will see today. And the secondary we are using this, these are gallium nitride from EPC. So these are low voltage GaN because that side is 48 volt. So I think these are 100 volt GaN, but the current is high, right? So a lot of conduction loss happens on that side. So you need to take care of all that, because the current is very high on the secondary. You have to do your inductor designs well. So that is how you can also find out the inductor current peak, RMS, and the transformer volt seconds that you need to design the transformer, right? So I'm not going into that detail. So you can see that this is the 3.3 kilowatt this. So here is the high frequency bridge is here, and I think maybe I'm wrong somehow. So this is that 400 volt inductor, and this is, there are two bridges. Is the Bharat there? Which side is the low one? This one. That is high voltage. This is the low voltage one. Right. So and here, unlike there, all bridges are switching at high frequency, and also the secondary is carrying a lot of current. So that's all. So we have tested it and it works, and I think the efficiency is somewhere 98% around that at 250 kilohertz. There is some problem that. So this is where the DC-DC completes. That bonus LLC I think is not possible. I will go to the traction inverter, right? Again from power electronics perspective. Can you change the? So any question that you might have? Turn-off losses are, IGBT turn-off loss is also high. Yes. See, IGBT, this, with IGBT you will not be able to switch more than 10 to 15 kilohertz. It will be very big converter. IGBT. People traditionally use MOSFET because here that diode reverse recovery problem is not there because you are going to avoid that hard turn-off.
Sir,
Yeah.
Yesterday you mentioned about the closed loop for PFC, that inner current and outer voltage. Here it is it like for constant current at constant current region there is one loop, and in constant voltage another loop.
Right. See, what is going to happen is, oh, we have changed it. Okay. See, the fundamental idea is that if you connect one element across another element, right? So say this is a resistance, right? The resistance decides the relation of the voltage and current across it. So this gives you one equation, V equal to IR. You cannot solve this. You have to also take this guy. This gives you two equations, and with that you can solve. Similarly, when in the battery, this is happening. If I force this current, battery will make the voltage this. I am not controlling this. I cannot control both voltage and current because the element decides. Element has an equation. I can force only one thing. Across a resistance, I can either force the current or I can force the voltage. I cannot force both of them. So similarly here I am controlling the current. Battery will make the voltage based on its cell condition, health, and all that people are talking about, right? Here I am making this voltage. Whatever current is drawn by the battery is drawn by the battery. That I have no control. But voltage into current is the power. So in that, this outer loop, right? So, yeah. So here what is happening is that the voltage into current is the power that I want to extract from this side. correct? So now when I am in the constant voltage region, I will use this loop. The loop will tell me what is the power required so that I can maintain this voltage, right? And when you go to constant current, you tell the current, you put the current reference, automatically it will take out that power and set the voltage, because then you are pushing that current. See, there is no DC current through that capacitor, right? If you pull that current and give it to the battery, automatically battery will set that voltage, right? So like that. So I don't actually have to, yeah, you have to switch the loops. You have to switch the loops. Essentially, you have to just change this reference. That's all, nothing much. Huh.
How do we calculate about the thermal design for the GAN device? Like, is it any different from, let's say, IDC devices or
No.
temperature and all those?
No, it's same man, same. See, the thing is that in thermal design, what you need to do is, I need to tell you what is the loss, how much loss it has to handle, take out, and I have to tell you the ambient temperature, right? And then I know based on that loss, and say I want to, like yesterday that equation I was telling, no, that say you have the device, right? So this is the case, right? So this is that heatsink material, say TIM, and this is your heatsink, right? This is your heatsink. So I know that junction is the loss into our junction to case plus T case, right? So I sort of know, I know this based on the operation, and I know here it goes like ulta, it goes, and I want to maintain this at 150 into 0.7, right? 150 is maximum, I will 70%. So then I know what is the power and what is the TC. So then, you know, then it is the, this is the R of TIM, and this is your R of heatsink, right? And then here is the ambient. So customer tells you the ambient. So ambient say 60C, customer tells you. From this equation, you know what is TC here. Maybe it comes out to be, given the power loss and our RJC from the device data sheet, this comes out to be say 80C, right? So then you put 80C here. This is given, and also you know the power loss, right? You know the power loss from your calculation or simulation and all that. So finally, in this, what we do not know is RHS, right? This is the thermal design. I need to figure out how to achieve that RHS, right? That is essentially so there is no difference in the basic understanding, but the challenge is that it is, you know, I think it is like 5 or few millimeter by few millimeter you have seen in the lab. So how to take out the heat from there is difficult. So what we are doing is we are using this top cool devices, where, you know, the thermal is one side and electrical is other side. So if we use electrical and thermal both the same drain, then the heat has to flow through the vias through the PCB. That we have found that, you know, it is not very effective. It puts large resistance in thermal resistance in between. So actually there is a lot of engineering that is difficult to discuss. Okay, so we will try to, okay, so the last one, right? So that is the, let's see how fast we can do this. I think it is very easy to see from the DC machine perspective. So okay. So we will get into this, but I will just quickly review here. See, what we are doing is, in this, my target is not to understand how the machine works or how to design the machine, right? I'm very particular about, I have like another 10 minutes. I'm very particular about designing that motor controller, right? How to design that, right? And what it should do. And any power electronic converter that I discussed already starts with the specification, then I tell you what is the topology, and then I tell you the switching strategy, and then I tell you the closed loop control, and once I have all that, I go to the design. That is the standard. Here also we will take the same thing, right? But, and the thing is that again I will stick to the two-wheeler example, and I'm talking about a motor which is a 3 kilowatt motor, right? I think no, it is a lower power motor. It doesn't matter, it is a 2 kilowatt motor, and it's a brushless DC motor, 8 pole, and RPM is 3000. Maximum torque that it can generate is about 6 Newton meter. So this is a very specific, this you will find this kind of motors, and usually we are all using brushless DC machine in this, right? So now brushless DC machine from the dynamics perspective is nothing different than the regular DC machine. Exactly the same, actually. So only thing is that in the regular DC machine, my magnet is fixed in the stator and conductors on the rotor. So the moment based on the position where the coil is with respect to the magnet, I switch with the brushes. But if I put the same DC machine with the windings on the stator and magnet on the rotor, the basic interaction torque, nothing changes because it's just the reference frame change. But now, based on the position of the magnet, before magnet was fixed, the coils were moving. Based on the position of the coil, I need to switch that coil. But now, I am putting the magnet in the rotor and the coils on the stator. So now, basically, with respect to the position of the magnet, I have to figure out which phase to switch, which coil to switch. That is basically what happens, right? So now from the control perspective, I have the slides, but I would like to just first discuss the basic DC machine employed in a EV, how to operate it, right? So essentially, what I will discuss is separately excited DC machine. Okay, so what happens there, right? So essentially, what happens is that, see, what is the output? Output of the motor is torque speed, right? So motor applies torque, load decides what will be the speed. So like the power supply, we apply voltage, load decides current, or the other way. So motor applies torque. So what has to happen is that this is your speed and this is your torque, right? So what happens is that when you are in standstill and you are starting, right, you want to accelerate. So they tell you, how fast you go to the top speed, right? So then the idea is what you want to do is you want to apply maximum torque, right? I think this is time, right? You try to apply the maximum torque you can, right? And accelerate. So the speed keeps increasing, right? And then probably you reach some speed. But what happens is from the motor's perspective that I will discuss immediately, it is difficult to continue to increase the speed. It is difficult. So there is a base speed at which you will go, right? So once you go beyond that speed, what you have to do is your torque has to fall. Right? And why does that happen? So basically, in DC machine, if you just look at the, we will need this in this discussion. So what happens is that, this is the induced voltage and this is your applied voltage. In steady state, there is a resistance which I will neglect right now. This is the voltage that in the terminal you are applying, and this is speed. So essentially, there are two equations. One is that your voltage equation, if I neglect this drop, Vt is actually equal to E, correct? Induced voltage. The applied voltage is same as induced voltage. And if you see, this guy is actually your flux into speed, right? It's a back EMF, right? It's a function of speed. And then you have your torque. The torque is essentially flux into current, armature current, right? So when I am trying to apply maximum torque, so these are the just two equations that we need to look at. So when I have been asked to apply maximum amount of torque, right, what I have to do is I have to tune this, make this maximum, right? So let's say I have also a field circuit, right, where I can actually control this phi by applying some voltage, right? So that IF, right? I am just talking about the basic idea, right? So what you would like to do is you want to see more I is a problem because of the conduction loss. So you would like to get the maximum torque keeping the maximum flux, right? And then what you do is, so this is max, then this is also max, this is also max. So you sort of design the machine so that the maximum current, this is also tuned to maximum, correct? This is what you do. And then what happens is, because you know there is this other equation, J d omega dt, you know this is equal to the applied torque by the motor minus the load torque, right? So basically, when you apply this torque, the speed starts increasing, right? The speed will start increasing because you are accelerating. The speed will start increasing. But if your speed keeps increasing, what is happening to your terminal voltage? Your terminal voltage is also increasing. You have tuned this to max, and your terminal voltage is also increasing with the speed. So now there is a point comes where the terminal voltage is maximum. I cannot apply that much terminal voltage at the top. So this is what we call base speed. This speed is that base speed, omega b we call. So once it hits the base speed, now still if I have to increase speed, what I can do? I have to drop my flux, right? This is called field weakening. So I will drop my flux so that speed can still go up for the same voltage. Now the voltage becomes constant. Actually, this is the voltage. That's why. So this is the terminal voltage. So terminal voltage will flat out after this, right? But the speed is keep increasing. Speed is still increasing, right? So, and you know, but as the flux has dropped, now torque is going to also drop. Even if you tune it to the maximum current, it cannot remain as the same torque there, right? So that is basically the drive cycle or whatever happens, right? This is exactly what happens, right? This is what, so we have to do something so that we can achieve this, right? And this dynamical equation and everything is same in the brushless DC machine, nothing much different. I will tell you exactly what is different from the drive perspective, but this is what exactly you would like to do. First, you would like to do a current control, like that CC. You want to do a current control and push the maximum amount of torque. And then once you reach the base speed, you will go in the flux weakening, right? So this is what we will do. So here is an example of a brushless DC machine that you can see that this is a practical, this is some Chinese make BLDC machine. And so what is happening here is, by the way, I should write now this, again, just if you look at the DC machine, right? This circuit is the armature circuit. In dynamics, we have to also consider the L of that when you are changing, right? So essentially that equation is Vt equal to R into Ia plus L dIa dt plus E, right? So that is the equation, right? So the thing is that BLDC machine exactly looks like that, like what he is drawing here. I will tell you what has to be done with the three-phase bridge here. So actually what happens is that when you are actually running this machine, right? Now this is the topology picture. My first thing after specification we come to topology, right? It is a basic three-phase bridge. So here you are connected to this brushless DC machine. So now we will first understand the operation, how to switch those switches, right? That is what we have to do. We have to understand how to do that, right? So let us see how to do that. So what happens is, if say you are running this machine, right? I told you, no, here the magnet is in the rotor, so I need to sense the position of the magnet. So there are these Hall sensors are there. So 3 Hall sensors are there, right? So those 3 Hall sensors, based on the position of the rotor, will tell you that this is the picture of the phase current. Okay, this square wave, quasi square wave, 120 degree quasi square wave. How this is happening, I am not getting into. Not required to understand the drive, right? To understand the drive, we have to understand that I have to ensure by switching that bridge that each phase currents are like flat top 120 degree, right? So I will come to this, say for example, and what will happen, and if you do that, the voltage that will be induced in the phase on the other side, that is the back EMF that I am talking about, will look like something like this trapezoidal waveform, right? So if you actually look at this carefully, what is happening is that always, if you see this 120 degree, you will see a pattern. You see that A phase current is positive for 120 degree. That time, the B phase current is negative for 160 degree, and C phase current is negative for another 60 degree. And this is what repeats, right? So always for total 120 degree, so total is 360 degree, out of that 120 degree, one phase current has to flow and be constant. At what value it should be constant, we will come later, but it should be constant, right, for 120 degree. And during that 120 degree, when 160 degree one leg and in the other 60 degree another leg, current is going to be negative, right? So now again, this is, so we are considering now just one of that 60 degree, right? You see in this particular 60 degree, IA is positive, right? And IB is negative and IC is 0. So that means in every 60 degree, only 2 legs are conducting. The other leg is not conducting, right? Only 2 legs are conducting, other leg is not conducting. And one leg is conducting positive, another leg is conducting negative, correct? That clearly we see. So that means that during this time, only A and B leg are going to switch and carry current. C leg is silent. And how to know in what 120 degree I am? That comes from your Hall sensors. Hall sensors actually will tell you when you have to make this current and this current. That information is coming in real time from Hall sensor, right? So the thing is that when I am here in this zone, what I am going to do is I am going to keep the top switch of this leg on permanently for this entire 60 degree, okay, and let it carry that current, okay. Now here the bottom switch has to carry the current, right, because this current is negative, the bottom switch will be carrying that current. Now if I was feeding this with a current source, then I will just carry this current and take it out, right? But I am feeding this with a voltage source, right? So remember, this is exactly the situation we have seen in case of PFC. One side I had grid voltage, here one side I have this EA plus EB. Other side I can actually, across AB, I can actually apply a PWM voltage because I have the bridge, right? And I can control that voltage and control the current. Is exactly same as the PFC. Remember, that bridge, I was applying a controllable voltage in that bridge. There was an inductor and there was a voltage source on the other side. Here that voltage source is back EMF. Picture is same. And I have an H bridge here. Again, same. There also we had an H bridge. The way you are switching is a bit different, right? So now what I am going to do is, I will keep this permanently on, but I have to somehow make this current look like DC like that, and to a particular value. Where I will get that value, I will come to that, Right now let's say I am telling you make it 20 ampere, right? So how we will do that? So how we are going to control this applied voltage VAB on the other side is by controlling the duty cycle of this switch. Okay, so when you turn on this switch, you see what is the AB voltage you are applying? What is the AB voltage you are applying? VDC. It is VDC, right? The VDC is getting applied, and when you are just turning off that switch, current is all positive. Then this diode is going to conduct. The top diode of that leg is going to conduct, and what is the voltage you are applying? 0. So over this, if I do a high frequency switching of this bridge with a particular duty cycle, that duty cycle let's say D6, right? By controlling that duty cycle, I can control the value of that current and I can keep it constant, right? So is this point clear? This is all connected. This again is a buck converter here, right? The same thing that we have done for PFC, we are again doing here, right? Yeah. So now what all I am telling you that using the bridge, how can you make the current look like this? Correct? See, all I am saying is how to switch that bridge so that current becomes flat top like that, right? How to decide the duty cycle of this negative or the bottom switch, that will come from closed loop, like it came there also from closed loop, the duty cycle, right? So actually if you see, if you look at this, the DC machine equations are like that. Here what happens is that if you look at at any point in that DC machine, these two are the back EMF, and in steady state you can sort of neglect these drops, right? Like I was doing here, right? So this is the 2E is the induced voltage in this. E plus E, it is coming on the negative, so it is becoming E plus E, right? So 2E is your this E, right? Which is a function of, this is the permanent magnet is the flux here and the speed, that is your back EMF, right? And the current here is this current that is flowing, that is your actually the armature current. The same current multiplied by flux will give you the torque. So essentially that flat top current, the flat top, what should be the current should come from your torque requirement, right? That should come from your torque requirement. So if you actually see, so essentially if you are doing a speed control, let's say you are doing this and this, right? You can do a torque control also without doing a speed control, then you can directly put the torque command here. But if you are doing a speed control, we have actually, there is this mechanical system, right? He is not showing the TL here. TL is a disturbance input. So applied torque and the inertia decides what is your speed, right? So here what I do is I have a reference speed. You sense the actual rotor speed. You calculate the error, give it to your controller. Controller should tell you what torque to apply, right? To achieve that speed, right? So you have that. So you got the torque constant, right? What torque, sorry, the torque reference. The outer speed loop will give you the torque reference. Probably if you are operating here, you don't need an outer speed loop. You can directly apply the torque, right? But once you go into this region, then you should try to control the speed or vice versa. So now what happens is, so this is the outer speed loop. This outer speed loop, if you divide by that constant, that K is that phi constant, you actually don't have to divide, closed loop will take care of it, will tell you what is the current, because torque is same as the current. And this current I star is that flat top, right? So now given the Hall sensor position, you can actually find out, and also you know the flat top, you know the Hall sensor position, then you can find out the current, reference current signal, that 120-degree current signal in time, right? So now this should go to a current loop. That current loop will decide the duty cycle and make that current same as the reference current. So that is the idea. So here also you see this is going to the current controller, and then from there you will go get all the duty cycles, right? So the thing is that, you know, then we have this equation, Vt equal to RIL di dt, that is that. 2R2L is coming because always two phases are in series coming in between line to line, right? So basically, you know, you are, say for example, now you are doing the A phase current. So then A phase current should go to the PI loop and should tell you what is the voltage, and that sort of give you the duty cycle, right? So that is how it will happen. So now the question is that we have understood the closed loop for this guy. We understood the closed loop, we understood how to modulate it, how to do the closed loop we understood in theory. And now once you know how the currents are, right, you can calculate, and here switching is happening, you know where the switching is happening. Then I told you, last the AC/DC thing, right, how to compute the switching loss, how to compute the conduction loss. You can compute all that and you can check whether a particular switch is good for you or not, right, or at what is the switching frequency you can actually switch, right. Those things will be decided from there, right. So you get, and here I don't have to actually, you know, design any filter or anything, but this capacitor has to be designed. This capacitor is going to see some switching current that needs to be designed. So I think I'm going to stop here, and quickly you can take your tea and go. Yeah. Here it is not required. No? It is just the DC machine. Just the DC machine, not required. You are just shaping a flat top current. DC current, just shaping the DC current. It is DC machine, perfectly DC machine, same as that. Only thing is there is the Hall sensor tells you which bridge, which leg, which current.
Sir, in this motor we have the magnets in the rotor. So to go beyond the base speed, are we demagnetizing the magnets?
This is a very good question. So you know how to demagnetize. See, the thing is that here the flux is constant, right? It is coming from the magnet. So how I am going to demagnetize?
Armature reaction?
Not really armature reaction, I think. So what you can do is, this is a very interesting idea. So, you know, the idea is same as how they do, okay, I will just tell you, it will take 1 minute. I am just drawing a basic single two-pole DC machine, okay. So here you have north pole, here you have south pole, right. So if you look at the rotor conductors, right, so these are all carrying positive current and these are all carrying negative current, right. These are all the coils, right. So now what is happening is here, this is the brass axis, right. So all coils are connected in series. So this positive current with N and negative current with S gives you positive torque, right. And voltages are also like that. But now once say it is moving, right. So say it is moving in this direction. Now this guy has to actually commute. Here the moment this goes here, the current should become negative here and positive here as it moves, right. And I need to commute this guy. But now say for example, here if I don't commute it to this point and I change the brush to this point, little bit I move the brush from the 90 degree, right. So then what will happen is, instead of getting all through positive current, you will get little bit of negative current here and negative current, positive current here, right. What that will mean? That will mean, and all these coils are connected in series. So that means now I am actually, before I was adding, say there are n coils, each were induced EMF E, right. So it was n into E. But now if I just move one coil position, it will become n minus 1 into E. Because one coil now is subtracting, and also torque will reduce. Because now I have some negative current with positive this thing, and positive current with S, right? So so now what you can do is you can actually forward the Hall sensor position. Hall sensor position you will get, but instead of following the Hall sensor position, you are not going to follow the reference exactly like that. So say for example, the Hall sensor is telling you do it like this, but instead of that you will make the current here like that. You will give a phase shift. And then it will create a negative torque. So actual torque will reduce, and also voltage also will reduce, the flux will reduce, right? So that is I think they call it brush. I can send you a paper. Old paper is there. If you email me, I will send you the paper. Right, how they do it.
Sir, upon
That's a
base
very good
speed, how
question.
much speed we can go, sir, in the field weakening?
See, the thing is that actually I will tell you honestly, I do not know because I have not designed this yet. But we have a project coming up where we are going to do this design. But so I really tell you, I do not know how they decide what will be the base speed and what is the base speed they will call and then where it will go. I do not know. It's a very good question.